Planet 9, a mysterious and unseen world lurking in the farthest reaches of our solar system. Its existence remains a tantalizing possibility, a shadowy enigma that defies detection. Yet its gravitational influence hints at a profound secret shaping our celestial neighborhood. The idea of an undiscovered planet isn't new. For centuries, astronomers have speculated about unseen forces influencing the motion of distant celestial bodies. But what makes Planet 9 different is the compelling evidence rooted in mathematics and physics that suggests something massive is out there. In 2016, a pair of astronomers, Konstantin Batygin and Mike Brown, proposed the Planet 9 hypothesis. They noticed a peculiar clustering of orbits among objects in the Kuiper belt, a vast region beyond Neptune. This unusual alignment couldn't be explained by chance alone, pointing to the gravitational pull of a hidden giant. If Planet 9 exists, it would be unlike anything we've encountered in the solar system. Estimated to be 10 times the mass of Earth, it would dwarf all other rocky planets. Its orbit would stretch hundreds of times farther from the Sun than Neptune, plunging it into an icy realm of darkness and cold. Despite its predicted size, Planet 9 remains invisible to our telescopes. Its incredible distance means it reflects very little sunlight, making it faint and elusive. The search for this ghostly planet has become one of the greatest challenges in modern astronomy, testing the limits of our technology and ingenuity. Some scientists argue that we're not just searching for a planet, we're unraveling the dynamics of the outer solar system. The unexplained patterns in the Kuiper belt suggest a story of gravitational interactions spanning billions of years. Planet 9, if real, could hold the key to understanding these cosmic mysteries. The hunt for Planet 9 is a race against the vastness of space. Telescopes around the world are scanning the sky, focusing on regions where its faint light might be detected. Computer simulations and cutting-edge algorithms are helping narrow down its possible location. But the task remains daunting, like finding a needle in a cosmic haystack. Not everyone is convinced. Alternative explanations challenge the need for a ninth planet. Some suggest the clustering in the Kuiper belt might be caused by smaller objects working in concert. Others propose we might be witnessing the effects of phenomena far beyond our understanding, like dark matter. Whether Planet 9 is real or not, its story captivates both scientists and dreamers alike. It represents the uncharted frontier, a reminder that even in our own cosmic backyard, there are still secrets waiting to be uncovered. And so the search continues. Astronomers push the boundaries of observation, determined to solve this celestial mystery. Every data point, every anomaly, brings us one step closer to answering the question, is there truly a ninth planet? In the early 19th century, astronomers began to notice peculiarities in the orbits of Uranus and Neptune. These irregularities hinted at the possibility of an unseen gravitational force, sparking early speculation about hidden celestial bodies in the outer solar system. This search led to the discovery of Pluto in 1930, a monumental find at the time. However, Pluto's size and mass turned out to be far too small to account for the orbital anomalies observed in the gas giants, leaving the mystery unresolved. As telescopes improved, astronomers continued probing the distant reaches of the solar system. They found a wealth of icy objects beyond Neptune, now known as the Kuiper belt. This region introduced new questions about the gravitational forces shaping its structure. By the late 20th century, the idea of an additional planet gained traction once again. Astronomers theorized that something massive could be lurking far beyond Pluto, influencing the orbits of both the gas giants and distant Kuiper belt objects. The term Planet X was coined to describe this hypothetical world, representing the unknown. Over the decades, searches for Planet X evolved, driven by technological advances and a growing understanding of celestial mechanics. One of the pivotal moments came with the realization that Pluto wasn't alone. The discovery of Eris in 2005, a Kuiper belt object similar in size to Pluto, further challenged the traditional view of the solar system and revived interest in the search for additional planets. Eris's discovery also played a role in redefining what constitutes a planet. While this demotion of Pluto to dwarf planet status made headlines, it highlighted the complexity of our solar system's outer regions and the need for further exploration. In parallel, researchers were uncovering new patterns in the orbits of trans-Neptunian objects. Some of these bodies displayed clustering behavior, which seem to defy conventional gravitational models without the influence of a large, unseen planet. The idea of a ninth planet was no longer fringe science. It became a serious topic of study, blending observations, computer modeling, and mathematical predictions to propose an object that could explain these orbital anomalies. Throughout history, this quest has been shaped by both triumphs and frustrations. Misinterpretations of data and the vastness of space often led to false starts, but each misstep contributed to refining the search methods and theories. The search for Planet 9 is also deeply rooted in humanity's broader curiosity about the unknown. For centuries, the drive to find new worlds has pushed the boundaries of science, compelling astronomers to question and redefine their understanding of the cosmos. This journey, marked by breakthroughs and reimaginings, underscores the evolving nature of planetary science. While the concept of Planet 9 has transformed over time, the fundamental question of what lies beyond remains as captivating as ever. The search for Planet 9 owes much to the work of Konstantin Batygin and Mike Brown, whose groundbreaking research reignited interest in the mysterious object. By analyzing the orbits of distant Kuiper belt objects, they provided mathematical evidence that strongly suggested the presence of a massive, unseen planet. Mike Brown, renowned for his discovery of Eris and other trans-Neptunian objects, brought his expertise in the outer solar system to the forefront of this investigation. His work reshaped our understanding of planetary dynamics and contributed to the reclassification of Pluto. Konstantin Batygin, an astrophysicist and theoretical modeler, played a pivotal role in calculating the potential orbit and characteristics of Planet 9. His contributions combined rigorous mathematics with creative problem-solving to reveal the plausibility of such a distant world. The duo's collaborative efforts began with the realization that several trans-Neptunian objects exhibited unusual clustering in their orbits. This pattern could not be easily explained without invoking the gravitational influence of a massive distant planet. Their 2016 paper proposed that this hidden planet, roughly 10 times the mass of Earth, resides in a highly elliptical orbit far beyond Neptune. The publication sparked a surge of interest and launched new searches across the global astronomy community. Beyond Batygin and Brown, other researchers have made significant contributions to the Planet 9 hypothesis. Chad Trujillo and Scott Shepard were among the first to notice the unusual orbital alignments in trans-Neptunian objects, laying the groundwork for later studies. Trujillo and Shepard's observations highlighted the need for further exploration of the Kuiper belt. Their early research served as a catalyst, encouraging other scientists to delve deeper into the outer solar system's mysteries. The work of mathematicians like Rodney Gomes also added weight to the hypothesis. Gomes proposed that an unseen planet could explain certain anomalies in the orbits of distant celestial bodies, offering a framework for interpreting observational data. Computer modeling by astronomers such as Renu Malhotra has also been instrumental. Malhotra's simulations suggested that a large planet could sculpt the orbital architecture of the Kuiper belt, supporting the notion of Planet 9's influence. In addition, the contributions of amateur astronomers and data scientists cannot be overlooked. Crowdsourced analysis and public involvement in telescope surveys have expanded the scope of the search, enabling researchers to cover more ground. The collaborative nature of this effort underscores the importance of teamwork in solving cosmic mysteries. By combining observations, mathematical models, and cutting-edge technology, researchers have pieced together a compelling case for Planet 9. While the hunt for Planet 9 continues, the foundational work of these key researchers remains vital. Their insights and discoveries have provided a roadmap, guiding current and future efforts to uncover the secrets of this elusive world. The Kuiper belt is a region teeming with icy bodies and dwarf planets, but its dynamics reveal puzzling anomalies. Some of the most distant objects follow highly elliptical orbits that seem unnaturally aligned, suggesting the presence of an unseen force. This alignment is not random. It appears as though these objects are being shepherded into specific paths by the gravitational influence of something massive, far beyond Neptune. Astronomers have also noticed that certain trans-Neptunian objects exhibit perihelion clustering. This means that their closest approaches to the Sun all occur in a similar direction, defying expectations for a chaotic and random distribution. The orbits of these objects are tilted at unusual angles relative to the plane of the solar system. This inclination further supports the idea that a distant gravitational force is shaping their trajectories over millions of years. One of the most intriguing observations is the existence of extreme trans-Neptunian objects. These bodies, located on the outskirts of the Kuiper belt, have orbits that can only be explained by the pull of a planet-sized object. Without the influence of an external mass, these distant objects should scatter over time due to gravitational interactions with the known planets. Yet their orbits remain surprisingly stable and consistent. Another anomaly is the apparent lack of objects in certain regions of the Kuiper belt. This absence, known as a gravitational gap, could indicate that a large planet has cleared these areas over time. Simulations of the Kuiper belt show that the gravitational effects of the known planets alone cannot reproduce the observed orbital patterns. These findings suggest the presence of an additional massive body exerting influence from afar. There are even objects on highly eccentric, almost comet-like trajectories that don't conform to the standard models. These paths hint at interactions with something massive, far beyond the reach of Neptune. In addition to these patterns, there's evidence of a mysterious clustering of orbital planes. This phenomenon cannot be explained without introducing the concept of a hidden planet affecting the overall structure of the belt. The lack of randomness in the Kuiper belt's configuration has led many astronomers to conclude that we're missing a key piece of the puzzle. Planet 9 provides a plausible explanation for the complex and unexpected orbital behavior. These anomalies continue to drive the search for answers. Each discovery brings us closer to understanding the unseen forces shaping the outer reaches of our solar system, with Planet 9 remaining a leading candidate. Mathematical models have been at the core of the Planet 9 hypothesis, providing a framework to interpret the anomalies observed in the Kuiper belt. Using simulations and calculations, researchers have mapped out how a massive distant planet could produce the gravitational effects we see. These models rely on Newtonian mechanics and perturbation theory, allowing scientists to understand how an unseen object could influence smaller bodies in the solar system over time. The results consistently point to the existence of a planet roughly 10 times the mass of Earth. Simulations show that the clustering of trans-Neptunian objects can be replicated by introducing a large planet into the models. Without this addition, the observed orbital patterns fail to emerge, strengthening the case for Planet 9. The models also predict the orbital properties of this hypothetical planet. Planet 9 is thought to follow a highly elliptical path, taking thousands of years to complete one orbit around the Sun. Its distance from the Sun places it well beyond the reach of most telescopes, but the gravitational imprint it leaves behind aligns with the behavior predicted by these mathematical frameworks. This provides indirect but compelling evidence of its existence. To test these predictions, astronomers input data from observed objects into complex computer programs. The outputs often match the theoretical effects of a massive planet, offering a consistency that would be difficult to achieve through chance alone. Planet 9's proposed orbit also helps explain the tilt of the entire solar system. Models suggest that the planet's gravitational influence over billions of years could be responsible for the slight misalignment between the Sun's equator and the orbital plane of the planets. Another fascinating result of these models is the prediction of how Planet 9 affects the distribution of objects in the distant solar system. It could act as a gravitational shepherd, herding some objects into specific orbits while ejecting others into interstellar space. The models further predict the existence of objects in retrograde orbits, moving opposite to the usual direction of planetary motion. Observations of such objects lend additional support to the idea of an unseen planetary force. Advanced mathematical techniques, including statistical analysis, have been used to rule out random chance as an explanation for the observed patterns. The likelihood of such alignments occurring without Planet 9 is astronomically low. These predictions are continually refined as new data becomes available. Each discovered trans-Neptunian object adds to the data set, enabling researchers to improve the accuracy of their models and narrow down the possible location of Planet 9. Mathematical modeling has become an indispensable tool in the search for this elusive planet. It bridges the gap between observation and theory, providing a roadmap for future discoveries while reinforcing the plausibility of Planet 9. Not all astronomers are convinced that Planet 9 exists. Some argue that the evidence supporting its presence could be explained by biases in observational data, rather than an undiscovered planet. One counter-argument suggests that the clustering of trans-Neptunian objects may not be statistically significant. If these objects were discovered in regions of the sky where telescopes are frequently pointed, their orbits might only appear to be aligned. Others propose that the gravitational effects attributed to Planet 9 could instead be caused by the combined influence of many smaller objects. These objects, collectively known as a disk or swarm, might produce similar orbital patterns without requiring a massive planet. Dark matter is another intriguing explanation offered by skeptics. Some theorize that the gravitational anomalies in the Kuiper belt could be the result of interactions with a clump of dark matter, rather than a physical planet. Another critique questions whether the models used to predict Planet 9's existence are overly simplified. Simulations rely on assumptions about the distribution and behavior of celestial objects, and small inaccuracies could lead to incorrect conclusions. There's also the possibility that we're misunderstanding the physics of the outer solar system. The region beyond Neptune is largely uncharted, and unexpected phenomena could be influencing the orbits of distant objects in ways we don't yet understand. Some researchers point to historical precedents where similar predictions failed. For example, the search for Planet X in the early 20th century was ultimately debunked, as the observed anomalies were later explained by better measurements of Neptune and Uranus. Another issue raised is the lack of direct evidence. Despite extensive telescope surveys and advancements in technology, no visible trace of Planet 9 has been found, leading some to doubt whether it exists at all. The vastness of the outer solar system presents additional challenges. The sheer difficulty of detecting faint objects at such great distances makes it easy to overlook alternative explanations that don't involve a massive planet. Skeptics also question why Planet 9 hasn't influenced the orbits of closer planets in more noticeable ways. If it's as massive as predicted, its gravitational effects should extend into the inner solar system, yet no such perturbations have been observed. There's ongoing debate about whether the evidence for Planet 9 might be explained through chaotic dynamics. Some argue that the outer solar system is more complex than current models account for, with no need to invoke a hidden planet. Despite these counter-arguments, the hypothesis remains a central topic of discussion. While skepticism challenges the prevailing narrative, it also drives researchers to refine their methods, ensuring that every possibility is thoroughly explored. Planet 9 is estimated to be about 10 times the mass of Earth, placing it firmly in the category of a super-Earth. This size and mass make it significantly larger than any terrestrial planet in our solar system, but smaller than the ice giants, Uranus and Neptune. Its diameter is likely between 2 and 4 times that of Earth, a range consistent with known super-Earths discovered in other planetary systems. This size would allow it to exert a powerful gravitational influence on nearby celestial objects. The planet's mass gives it the ability to shape the orbits of distant trans-Neptunian objects. Its gravitational pull is thought to be strong enough to create the clustering patterns observed in the Kuiper belt over billions of years. Despite its estimated size, Planet 9 would appear faint from Earth due to its extreme distance from the Sun. This faintness makes it nearly invisible to even the most advanced telescopes, requiring careful analysis to detect. Its density is believed to be comparable to that of rocky planets, though it may also contain a significant amount of ice or gas. This composition would place it somewhere between a rocky super-Earth and a small ice giant in terms of its physical structure. Calculations suggest that Planet 9's surface gravity could be twice that of Earth's. Such gravity would allow it to retain a thin atmosphere, potentially composed of hydrogen and helium, similar to Neptune's outer layers. Given its mass, Planet 9 could have played a major role in the early formation of the solar system. Its gravitational effects may have shaped the orbits of smaller bodies and influenced the distribution of material in the outer solar system. The planet's large mass also raises questions about its origin. It may have formed closer to the Sun before being ejected into its current position by gravitational interactions with Jupiter or Saturn. Alternatively, Planet 9 could be a captured rogue planet. If it originated outside the solar system, its mass and trajectory could provide valuable insights into the dynamics of planetary capture. The estimated size and mass suggest that it might still be forming or cooling. If it contains a significant amount of ice or gas, its internal heat could influence its physical appearance and atmospheric behavior. Its mass would also affect how it interacts with passing comets and other debris. Planet 9 could act as a gravitational gatekeeper, deflecting objects toward or away from the inner solar system. Understanding its size and mass is critical for narrowing down its location. Theoretical models use these estimates to predict how Planet 9's gravitational signature would appear in astronomical surveys, guiding the ongoing search. Planet 9 is thought to follow an exceptionally elongated and elliptical orbit around the Sun. This unique trajectory places it hundreds of times farther from the Sun than Earth at its farthest point, a distance known as its aphelion. At its closest approach, or perihelion, the planet may still be much farther out than Neptune. Estimates place this distance at about 200 astronomical units, or 200 times the distance between Earth and the Sun. Its full orbit around the Sun is incredibly long, taking an estimated 10,000 to 20,000 Earth years to complete a single revolution. This vast orbital period is one reason why the planet has remained so elusive to astronomers. Planet 9's orbit is also believed to be tilted relative to the rest of the solar system. This inclination places it on a different plane, making it even harder to locate using traditional survey methods. The orbit's eccentricity, or how stretched out it is, suggests that the planet might spend most of its time in the distant reaches of the solar system. This would explain why it appears so faint and why no direct observation has yet been made. The alignment of trans-Neptunian objects provides clues about the orientation of Planet 9's orbit. These objects seem to cluster in ways that point to a specific region of the sky where the planet's gravitational influence might be strongest. Its distance from the Sun has profound implications for its surface temperature. With so little sunlight reaching it, Planet 9 would be one of the coldest objects in the solar system, with temperatures likely near absolute zero. The vast space it traverses in its orbit also raises questions about what lies beyond. If Planet 9 exists, it may mark the boundary between the solar system and the interstellar medium, a region filled with unknowns. Gravitational interactions during its formation or evolution may have pushed Planet 9 into this distant orbit. Some theories suggest it was ejected by larger planets in the early solar system, while others propose it was captured from a passing star. Its orbital properties also hint at potential interactions with other distant objects. The planet could be influencing the trajectories of comets, Kuiper belt objects, and even hypothetical bodies in the Oort cloud. By understanding its orbit, researchers can also refine estimates of its current position. Mathematical models use the planet's predicted path to focus observational efforts on specific regions of the sky. The extreme nature of Planet 9's orbit challenges traditional views of our solar system structure. It suggests that there may be far more complexity and diversity in planetary orbits than previously thought. Planet 9's composition is likely a mix of rock, ice, and gas, similar to the ice giants Uranus and Neptune. Its large mass suggests it may have accreted significant amounts of material during the early formation of the solar system. If it formed closer to the Sun and was later ejected outward, its composition might include a higher proportion of rocky material. This would make it distinct from the more gas-rich outer planets like Jupiter and Saturn. The planet's outer layers could contain frozen water, methane, or ammonia, all common ices in the outer solar system. These materials would likely remain in a solid state due to the planet's frigid environment. Beneath its icy exterior, Planet 9 could possess a rocky core, similar to what we see in other super-Earths. This core might generate heat through radioactive decay, influencing the internal dynamics of the planet. Its atmosphere, if present, would be extremely thin and composed mainly of hydrogen and helium. These light gases are remnants of the primordial nebula from which the solar system formed. Due to its distance from the Sun, any atmosphere it retains would be extremely cold and likely low in pressure. This would make it vastly different from the dense atmospheres of the inner planets, or the thick gas envelopes of Jupiter and Saturn. Some scientists speculate that Planet 9 could have trapped heavier gases like methane or nitrogen during its formation. These gases might now exist in trace amounts, frozen into its surface or mixed with its ices. The possibility of internal heat could lead to intriguing phenomena. If the planet retains any warmth from its core, it could drive subsurface activity, such as slow-moving currents within its icy mantle. Planet 9's overall composition might also depend on its origin. If it was a captured rogue planet, its material makeup could differ significantly from objects that formed within the solar system. The planet's cold environment means it likely reflects very little sunlight, contributing to its near invisibility from Earth. Its surface could be covered in dark, carbon-rich compounds, absorbing more light and making it harder to detect. Understanding its composition would provide clues about its history and evolution. By comparing its properties to other planets and exoplanets, scientists could uncover how it fits into the broader picture of planetary science. While much about Planet 9's composition remains speculative, its potential diversity highlights the complexity of the outer solar system. Each layer, from its rocky core to its icy surface, holds a piece of the puzzle waiting to be uncovered. Planet 9 is often compared to Neptune and Uranus due to its predicted size and composition. Like these ice giants, it's thought to contain a mix of rock, ice, and gas, placing it in a similar category of planetary types. Unlike Uranus and Neptune, Planet 9's orbit is vastly more elongated and distant. This extreme separation from the Sun sets it apart, making it more comparable to some exoplanets found in distant star systems. Its mass, estimated at about 10 times that of Earth, aligns it with the super-Earth class of exoplanets. These planets are larger than Earth but smaller than Neptune, a category commonly observed in other parts of the galaxy. If confirmed, Planet 9 would be the first super-Earth discovered in our solar system. This would bridge a gap between the types of planets we see here and those frequently identified around other stars. In terms of atmospheric composition, it might resemble Neptune with thin layers of hydrogen and helium. However, its colder environment and lower sunlight exposure could create unique atmospheric conditions not seen in the ice giants. Compared to Earth, Planet 9 would have much stronger gravity, reflecting its larger mass. This would make its surface environment far harsher and less likely to support life as we know it. Its orbit, taking thousands of years to complete, has similarities to distant exoplanets known as long-period planets. These objects often have extreme eccentricities, much like the predictions for Planet 9's trajectory. Unlike the gas giants of our solar system, which dominate their surroundings, Planet 9's influence is subtler. Its gravitational effects are primarily seen in the clustering of distant Kuiper belt objects rather than in shaping nearby planetary orbits. Compared to hot Jupiters found around other stars, Planet 9 is a stark contrast. While hot Jupiters orbit close to their stars, Planet 9 exists in an icy, dark realm, far from the Sun's warmth. Its composition might also resemble icy exoplanets discovered in other star systems, which often contain high levels of frozen water and methane. These similarities suggest that Planet 9 could provide a local analogue for studying distant worlds. The search for Planet 9 highlights an interesting gap in our solar system. While super-Earths are abundant in other planetary systems, this type of planet appears to be rare or hidden in our own. Studying Planet 9, if found, could offer a unique comparison to both known planets in the solar system and the diverse range of exoplanets beyond it. This connection would help us understand the processes that shape planetary systems everywhere. Planet 9 remains undetected largely because of its extreme distance from the Sun. At such a vast range, it reflects very little sunlight, making it incredibly faint and difficult to spot, even with advanced telescopes. Its predicted orbit places it in a sparsely studied region of the sky. Astronomers have only surveyed a fraction of the areas where Planet 9 might be hiding, leaving much of its potential path unexplored. The planet's slow movement across the sky further complicates detection. Unlike closer objects, which shift noticeably over short periods, Planet 9's motion would be so gradual that it could blend into the background. Modern telescopes, though powerful, have limitations when it comes to detecting faint, distant objects. Instruments like the Hubble Space Telescope or ground-based observatories are optimized for brighter targets closer to Earth. Another challenge is the sheer size of the search area. Planet 9's potential orbit spans a massive portion of the sky, requiring astronomers to methodically scan countless regions to locate even the faintest sign. If Planet 9 is covered in dark, carbon-rich materials, it may absorb most of the sunlight that reaches it. This would make it even harder to detect, as it would blend into the blackness of space. Dust and gas in the outer solar system can also obscure our view. Intervening particles between Earth and Planet 9 could further reduce its visibility, adding to the difficulties faced by astronomers. The planet's faint infrared emissions might be the best way to detect it, but even infrared telescopes have limits. At such a cold temperature, Planet 9 would emit weak thermal radiation, requiring highly sensitive instruments to capture. Another factor is the uncertainty in its exact position. Without knowing its precise location, astronomers must rely on probability and theoretical models to prioritize where to look. Its inclination relative to the solar system's plane could mean it's hiding in a part of the sky not traditionally searched. This tilt places it outside the paths of most observational surveys, further delaying its discovery. Competing sources of light in the distant sky, such as faint stars or galaxies, can easily be mistaken for Planet 9. Disentangling these background objects from a potential planetary signal requires meticulous analysis. Ultimately, the combination of its faintness, slow motion, and vast search area explains why Planet 9 remains undetected. Its discovery will likely depend on next-generation telescopes and refined search techniques to overcome these challenges. The orbits of certain Kuiper belt objects show patterns that are both striking and unexplained. These objects follow paths that cluster together in ways that defy expectations of random distribution. Many of these objects have highly elongated orbits, stretching far beyond the usual range of the Kuiper belt. Their trajectories suggest they are being influenced by a strong gravitational force from an unseen source. Another unusual feature is the alignment of their perihelion points, where their orbits come closest to the Sun. These points tend to cluster in one direction, which is unlikely to occur naturally without external interference. The inclination of their orbits also stands out. Some Kuiper belt objects follow paths that are tilted significantly compared to the plane of the solar system, hinting at a disruptive force acting on them. Some of the most extreme KBOs, with orbits extending far into the distant solar system, show signs of being shepherded. Their consistent orbital behavior suggests they are under the influence of a massive distant planet. These objects are not just clustered in their positions, but also in their orientations. This unusual consistency is difficult to explain without introducing the gravitational pull of an additional, yet unseen, planetary body. Simulations of the Kuiper belt using known planetary influences fail to recreate these orbital alignments. The introduction of a massive distant planet into these models successfully reproduces the observed patterns. Certain KBOs even exhibit retrograde orbits, moving in the opposite direction to most objects in the solar system. Such orbits could be the result of gravitational interactions with a large distant planet over time. The existence of detached objects adds to the mystery. These bodies are completely isolated from Neptune's influence, yet their orbits show signs of having been shaped by a powerful gravitational force. Some theories suggest that these unusual orbits could only have formed during the early solar system. A massive planet migrating outward might have scattered these objects into their current positions, leaving behind a gravitational imprint. The clustering and alignment seen in these KBOs are statistically significant. The chance of such patterns occurring without the influence of an external force is extremely low, reinforcing the argument for Planet 9. The peculiar orbits of these distant objects provide some of the strongest indirect evidence for the existence of Planet 9. They serve as a cosmic fingerprint, hinting at the presence of an unseen giant shaping the outer reaches of our solar system. The clustering of distant celestial objects in the outer solar system has become one of the most compelling mysteries in astronomy. These objects, far beyond Neptune, exhibit unusual patterns in their orbital paths that seem to defy randomness. Their orbits are not scattered uniformly across the sky, as might be expected in such a distant region. Instead, many of them appear to group together in specific directions, forming distinct clusters. One of the most striking features is the alignment of their elongated orbits. The farthest points of these orbits, known as their aphelia, tend to point towards similar regions in space, suggesting an unseen force at work. And this grouping is difficult to explain through the gravitational influence of known planets. The existing giants, like Neptune and Uranus, do not exert enough force at these distances to create such a concentrated pattern. Simulations show that this clustering becomes even more pronounced when a massive planet, like the hypothesized Planet 9, is included. The gravitational pull of such an object could explain why these distant celestial bodies remain grouped together. Another aspect of this clustering is its stability over time. Despite the chaotic dynamics of the outer solar system, these objects have maintained their grouped configurations for billions of years. The eccentricity of their orbits also stands out. Many of these objects follow highly stretched paths that are difficult to reconcile with standard models of solar system formation, unless a massive planet has been influencing them. Beyond their physical grouping, the orbital planes of these objects are similarly aligned. This uniform tilt adds another layer of complexity to the clustering, further supporting the idea of a hidden gravitational force. The clustering isn't just limited to one type of object. It spans a range of celestial bodies, from smaller icy fragments to larger trans-Neptunian objects, all showing signs of being guided by the same influence. Some researchers have explored alternative explanations for the clustering, such as interactions with a dense disk of material in the distant solar system. However, these theories often fail to match the precision of Planet 9's gravitational effects. This phenomenon isn't seen anywhere else in the solar system, making it unique to the region beyond Neptune. It raises questions about the dynamics of the outer solar system and what forces might be shaping it. The clustered orbits of these distant objects remain one of the strongest indirect signs of Planet 9's existence. They provide a map, pointing astronomers toward the potential location of this mysterious, unseen world. Computer simulations have become a vital tool in understanding the possible influence of Planet 9. By recreating the outer solar system in virtual models, researchers can test how a massive unseen planet might affect distant objects. These simulations show that introducing a planet roughly 10 times the mass of Earth can replicate the observed clustering of trans-Neptunian objects. Without this added planet, the patterns seen in the Kuiper belt do not emerge. Simulated orbits align remarkably well with real observations. When Planet 9's gravitational pull is factored in, the unusual eccentricities and inclinations of distant celestial bodies begin to make sense. The simulations also predict that Planet 9 would stabilize the orbits of certain objects over billions of years. This stability explains why some trans-Neptunian objects maintain their clustered configurations despite the dynamic nature of the solar system. Researchers have tested multiple scenarios to rule out alternative explanations. Time and again, the models that include Planet 9 provide the best match for the observed data, while models without it fall short. Simulations also help estimate the planet's orbit and location. By tweaking variables like its mass and distance from the Sun, researchers can refine predictions about where Planet 9 might currently reside in the sky. One unexpected result of these simulations is the prediction of objects in retrograde orbits. These backward-moving paths are rare and difficult to explain without the gravitational influence of a massive distant planet. The models show that Planet 9's presence could also explain why certain Kuiper belt objects are completely detached from Neptune's influence. Its gravity creates a barrier, shaping the outer edges of the solar system. Beyond clustering, simulations suggest that Planet 9 might periodically scatter smaller objects into the inner solar system. These interactions could explain the origin of some long-period comets. Advanced algorithms are used to run these simulations with increasing accuracy. By processing vast amounts of data, researchers can explore countless possibilities, narrowing down the most likely scenarios for Planet 9's existence. These tools also allow scientists to predict future discoveries. If Planet 9 exists, its gravitational effects should create patterns in the orbits of yet-to-be-discovered objects, giving astronomers specific targets to search for. The results of these simulations continue to strengthen the case for Planet 9. They provide a theoretical foundation that ties together observations, offering a plausible explanation for the mysteries of the outer solar system. Planet 9's gravitational effects extend far beyond the Kuiper belt, subtly influencing the solar system as a whole. Its immense mass, combined with its distant orbit, creates a gravitational field capable of reshaping the outer regions of the system. One of the most noticeable impacts is the clustering of trans-Neptunian objects. These distant bodies are corralled into specific orbits, their paths dictated by the planet's gravitational pull over billions of years. Its influence could also explain the tilt of the solar system's orbital plane. The entire system is slightly misaligned with the Sun's equator, and Planet 9's gravity may have caused this tilt through long-term interactions. Comets and smaller icy bodies are likely affected by its pull as well. Planet 9's gravity might redirect some of these objects toward the inner solar system, potentially influencing the rate of cometary activity near Earth. It may also act as a stabilizing force for certain regions of the Kuiper belt. Objects that fall within specific gravitational resonances with Planet 9 remain locked into predictable patterns, avoiding ejection from the solar system. Some simulations suggest that Planet 9 could act as a barrier, preventing certain objects from venturing closer to the Sun. Its gravity might effectively limit the inward migration of trans-Neptunian objects. Beyond the Kuiper belt, its effects could extend into the Oort cloud, the vast reservoir of icy bodies at the solar system's edge. Planet 9's presence may perturb this region, influencing the distribution of long-period comets. Its gravitational interactions might also explain gaps and voids in the outer solar system. Areas where objects seem mysteriously absent could be regions where Planet 9's gravity has cleared the space over time. The planet's orbit may periodically bring it closer to other outer solar system objects, causing gravitational disturbances. These interactions could lead to temporary changes in their orbits before they settle into new paths. Planet 9's mass allows it to act as a gravitational anchor, maintaining the overall structure of the distant solar system. Without its influence, some regions might be far more chaotic and unstable. Its interactions with the known planets are minimal due to its extreme distance, but they are not negligible. Over long timescales, its gravity might subtly alter the orbits of Neptune and Uranus, contributing to their observed motions. The gravitational effects of Planet 9 highlight its potential importance in shaping the architecture of the solar system. These interactions provide a window into the forces at play in the outer reaches, offering a deeper understanding of our cosmic neighborhood. Some researchers suggest that the clustering of trans-Neptunian objects might be explained without invoking Planet 9. Instead, they propose that a dense disk of small icy bodies in the outer solar system could produce similar gravitational effects. This disk, if it exists, would exert a combined gravitational force, influencing the orbits of distant objects. However, simulations involving a disk often fail to replicate the precise clustering patterns observed in the Kuiper belt. Others argue that observational biases could account for the apparent anomalies. If telescopes have focused disproportionately on certain regions of the sky, it might create the illusion of clustering where none actually exists. The possibility of a primordial black hole has also been raised. A black hole the size of a grapefruit, but with the mass of Planet 9, could exert the same gravitational influence while remaining undetectable through traditional methods. However, a black hole would produce unique signatures, such as lensing effects or radiation from surrounding material. So far, no such evidence has been observed, making this explanation less likely. Another theory involves interactions with passing stars. Early in the solar system's history, a close stellar encounter could have perturbed the orbits of outer objects, leaving behind the clustering we see today. While this scenario is plausible, it would require very specific conditions to produce the long-term stability observed in the orbits of trans-Neptunian objects. A massive, distant planet offers a more consistent explanation. The influence of dark matter has also been considered. Some scientists speculate that unseen clumps of dark matter in the solar system's outskirts could explain the gravitational anomalies, though this remains highly speculative. Another possibility is that we're observing the effects of a combination of smaller forces rather than one dominant influence. Multiple smaller objects or phenomena could collectively mimic the gravitational pull of a single massive planet. Despite these alternatives, the Planet 9 hypothesis remains the most robust explanation. Its gravitational effects align closely with observations, and simulations including it consistently produce results that match the data. Many of the alternative theories struggle to account for all aspects of the observed phenomena. While they explain certain features, they often fail to address the full range of clustering patterns and orbital alignments. The ongoing debate fuels the search for definitive evidence. Whether Planet 9 is real or another theory proves correct, the process of elimination brings us closer to understanding the mysteries of the outer solar system. Current telescopes face significant challenges in detecting objects as distant and faint as Planet 9. Their sensitivity is limited, making it difficult to pick up the weak light reflected by an object hundreds of astronomical units away. Planet 9's potential location places it in a sparsely illuminated region of the sky. Even the most powerful ground-based telescopes struggle to distinguish it from the faint background of stars and galaxies. The vast search area adds to the difficulty. With its predicted orbit spanning a large portion of the sky, telescopes must methodically scan huge regions, requiring substantial time and resources. Telescopes like the Hubble Space Telescope are designed for observing bright, well-defined targets. Detecting a faint, slow-moving object like Planet 9 is outside their optimal capabilities, limiting their effectiveness in this search. Infrared telescopes, while better suited to detecting cold objects, still face constraints. Planet 9's thermal emissions would be extremely weak, making it nearly impossible to spot without extraordinarily sensitive instruments. Atmospheric distortion is another challenge for ground-based observatories. Even with advanced adaptive optics, the faint light from Planet 9 can be blurred, reducing the chances of detection. The brightness of nearby objects can also interfere with observations. Stars and other celestial bodies in the same field of view often outshine potential signals from Planet 9, complicating its identification. Another limitation is the time required for repeated observations. Detecting slow-moving objects requires taking multiple images over weeks or months to confirm motion, which consumes valuable telescope time. Technological constraints in image processing also play a role. Algorithms used to search for faint objects sometimes miss subtle signals or mistakenly classify them as noise, delaying progress. Even the largest telescopes currently in operation lack the resolution to focus effectively on Planet 9's predicted location. Upcoming facilities may provide the needed clarity, but for now, these limitations persist. The extreme cold and faintness of Planet 9's potential surface reduce the contrast against the dark backdrop of space. This lack of contrast makes it incredibly challenging to detect, even with state-of-the-art equipment. Despite these challenges, advancements are on the horizon. The next generation of telescopes promises greater sensitivity and wider fields of view, bringing the search for Planet 9 closer to a breakthrough. Planet 9's extreme distance from the Sun places it in one of the darkest, coldest regions of the solar system. At hundreds of times the distance between Earth and the Sun, the light it reflects is incredibly faint and difficult to detect. This distance means the sunlight reaching Planet 9 is vastly diminished. With so little light available, even a large planet would appear as a dim point of light against the backdrop of space. Its faintness is compounded by the vast amount of space it occupies in its orbit. The planet could be anywhere along this path, and its light blends into the cosmic background, making it nearly invisible to most telescopes. Objects at such a distance reflect only a fraction of the sunlight they receive, and Planet 9's surface may be covered in materials that further absorb light. Dark, carbon-rich compounds could reduce its visibility even more. The lack of thermal energy from the Sun also makes it one of the coldest objects in the solar system. This frigid environment means its thermal emissions detectable in the infrared spectrum are faint and require highly sensitive equipment to observe. Its immense distance also affects how slowly it appears to move across the sky. This slow movement makes it harder to distinguish from stationary background stars, further complicating its detection. Even if Planet 9 were spotted, its faintness could make it difficult to confirm its identity. It would require multiple observations over time to rule out other explanations, such as a distant star or a faint galaxy. The faintness isn't just a limitation for optical telescopes. Radio and infrared observations face similar challenges, as the weak signals from Planet 9 must compete with noise from other celestial sources. Extreme distance also introduces uncertainties in its exact location. Without precise data, astronomers are left to search vast regions of the sky, making the process slow and resource-intensive. Planet the 9th of May spent most of its orbit at aphelion, the farthest point from the Sun. If it's currently near this part of its path, its already faint light would be even weaker, reducing the likelihood of detection. Its faintness and distance push the limits of current technology, demanding next-generation instruments for a breakthrough. The challenge lies not only in finding it, but in confirming that what is observed matches the predictions for Planet 9. Despite these obstacles, the planet's faint presence leaves a gravitational signature. Its influence on distant objects provides indirect evidence, guiding astronomers toward where it might be hiding in the vast reaches of space. Pinpointing the location of Planet 9 is a monumental challenge due to its immense distance and vast orbital path. Its highly elongated orbit means it could be anywhere within a massive expanse of space, making targeted searches extremely difficult. The predicted orbit spans a wide area, and without precise data, astronomers must systematically scan regions of the sky. This process is time-consuming and requires advanced technology to detect faint signals. Its position depends on where it is in its orbit, which could range from relatively closer perihelion to its distant aphelion. If it's near the farthest point of its orbit, the planet would appear even dimmer and harder to detect. The tilt of its orbit adds another layer of complexity. Unlike the known planets, which orbit near the plane of the solar system, Planet 9's path is thought to be inclined, making it harder to predict its exact location. Models provide only estimates of where the planet might be, based on its gravitational effects on other objects. These predictions narrow the search area, but still leave vast portions of the sky unexplored. Another factor is its slow movement across the sky. Because it takes thousands of years to complete one orbit, its motion is barely perceptible, making it blend in with the background stars. Background noise from distant stars and galaxies complicates the search further. Planet 9's faint light is easily lost among the countless celestial objects that populate the same regions of space. Astronomers must rely on repeated observations to confirm movement, requiring precise alignment and significant amounts of time. This makes it difficult to distinguish the planet from other stationary or slow-moving objects. Even when using powerful telescopes, the planet's faintness means its signal can be mistaken for an anomaly or dismissed as noise. Filtering through this data to identify a true candidate takes meticulous effort. The sky itself poses challenges, with some regions obscured by dense star fields or interstellar dust. These areas are more difficult to study, potentially hiding the planet from view. Planet 9's hypothetical location may shift as new data is collected. Each discovery of a trans-Neptunian object refines the models, but it also means adjusting and sometimes expanding the search area. This ever-evolving search requires collaboration, patience, and cutting-edge technology. While pinpointing Planet 9 remains elusive, each step forward brings astronomers closer to solving one of the solar system's greatest mysteries. The cosmos is filled with countless sources of light and radiation, creating a constant background noise that complicates the search for Planet 9. Faint stars, distant galaxies, and even interstellar dust can all mimic the weak signals astronomers are trying to detect. Planet 9's faint light is easily overshadowed by these brighter celestial objects. Its weak reflection of sunlight blends into the cosmic backdrop, making it almost indistinguishable without precise filtering techniques. Even in the infrared spectrum, where Planet 9's thermal emissions might be visible, competing signals from other sources can create confusion. Distant stars emit similar wavelengths, often masking potential detections. Closer to home, the Kuiper belt itself adds to the noise. This region is populated by countless small, icy objects that reflect light in ways similar to what we might expect from Planet 9. Earth's atmosphere contributes its own interference for ground-based telescopes. Atmospheric distortion and scattered light make it harder to isolate the faint signals of a distant planet from the background clutter. Space-based telescopes face their own challenges, with cosmic rays and sensor artifacts adding noise to the data. Every image taken must be carefully analyzed to rule out false positives caused by these distortions. The movement of other celestial bodies complicates long-term observations. Over time, stars and galaxies shift slightly in the sky, creating patterns that can be mistaken for a moving planet. Filtering through this background noise requires sophisticated algorithms and machine learning tools. These programs must be trained to distinguish the subtle signature of Planet 9 from the overwhelming volume of false signals. Sometimes the sheer density of stars in certain regions of the sky makes it nearly impossible to isolate individual objects. These crowded areas, known as star fields, are particularly challenging to search. Interstellar dust also contributes to the difficulty. It absorbs and scatters light, creating hazy regions that obscure faint objects, like Planet 9, from view. Even the telescope itself can generate noise. Minor imperfections in its sensors or optics can produce anomalies that mimic the faint signature of a distant object, leading to false detections. Competing background noise is one of the most persistent obstacles in the search for Planet 9. Overcoming it requires not only advanced technology, but also meticulous analysis and a deep understanding of the cosmos. Detecting Planet 9 will require advancements in telescope technology that go beyond what is currently available. Next-generation telescopes must be able to capture faint light signals across vast areas of the sky with incredible precision. Higher sensitivity sensors are essential to detect the weak light reflected from such a distant object. These sensors would need to minimize noise while amplifying even the faintest signals from the depths of space. Wide-field telescopes capable of surveying large portions of the sky in a single scan would significantly improve the chances of locating Planet 9. By covering more ground, these instruments can narrow down potential locations faster. Advances in infrared technology are also crucial. Planet Nine's faint heat emissions could be better detected with instruments that can capture extremely low levels of infrared radiation. Space-based telescopes hold particular promise as they operate free from atmospheric distortion. Future missions designed specifically to hunt for faint objects in the outer solar system could bring the search closer to success. Machine learning and artificial intelligence are becoming indispensable tools in this effort. These technologies can analyze vast amounts of data, identifying subtle patterns that might indicate the presence of Planet 9. Enhanced image processing techniques are needed to filter out background noise more effectively. By isolating the unique characteristics of Planet 9's signal, astronomers can better distinguish it from other celestial objects. Time-domain astronomy, which tracks objects over time, would benefit from more precise instruments. Improved tracking capabilities could confirm the slow movement of Planet 9 against the background stars. Collaborative networks of observatories around the world could pool their resources, providing continuous coverage of the sky. This global effort would increase the likelihood of capturing the planet's faint signals. Larger mirrors on ground-based telescopes would allow for greater light-gathering capability. The more light these mirrors collect, the easier it becomes to detect faint and distant objects like Planet 9. Improved software for orbital modeling would refine predictions of where Planet 9 might be. By incorporating the latest observational data, these models can guide telescopes to more precise search areas. To truly unlock the secrets of Planet 9, a dedicated mission to the outer solar system might eventually be required. Such a mission would carry instruments designed specifically to probe the planet's faint light and thermal emissions directly. Some scientists propose that the observed clustering in the Kuiper belt might not be caused by a single large planet, but by the combined gravitational effects of multiple smaller objects. These objects, scattered throughout the outer solar system, could collectively influence the orbits of trans-Neptunian bodies. If this is the case, these smaller objects would need to be distributed in a way that mimics the gravitational pull of a single massive planet. Their cumulative force could explain the unusual alignment of orbits observed in distant regions. This theory suggests that instead of one dominant Planet 9, there could be a swarm of icy bodies or dwarf planets exerting their influence over billions of years. These smaller objects, though individually weak, might work together to shape the orbital patterns we see. The Kuiper belt is known to contain a vast number of icy bodies, many of which remain undiscovered. If these objects are more massive than previously thought, their gravitational interactions could play a significant role in the structure of the outer solar system. Simulations involving multiple smaller objects have shown some promise in replicating the observed clustering. However, these models often require very specific distributions and masses, which may be less likely than the presence of a single large planet. One challenge with this theory is the lack of direct evidence for such a swarm. While many trans-Neptunian objects have been discovered, their combined mass appears insufficient to account for the observed gravitational effects. It's possible that these smaller objects are simply too faint to detect with current technology. If they exist, their extreme distances and low reflectivity would make them even harder to find than a large planet. The idea of multiple smaller objects aligns with the concept of a more chaotic, less structured outer solar system. Rather than being dominated by a single force, this region could be shaped by complex interactions among many smaller bodies. If confirmed, this theory would change how we understand planetary formation and dynamics. It suggests that the outer solar system might host a population of intermediate-sized objects, bridging the gap between known dwarf planets and full-size planets. This scenario might also help explain why no single large object has been observed. The gravitational influence could be spread across a wide area, making it harder to pinpoint a specific source. Despite its potential, this theory still leaves some questions unanswered. The specific alignment and stability of the orbits in question are more easily explained by a single massive planet than by multiple smaller ones. Further exploration of the outer solar system will be needed to test this hypothesis. Whether through advanced telescopes or future missions, discovering these smaller objects could provide critical insights into the forces shaping our cosmic neighborhood. Some researchers have suggested that the anomalies attributed to Planet 9 could instead be caused by a clump of dark matter. Dark matter, which does not emit or reflect light, could create the gravitational effects observed in the outer solar system without being directly visible. If a dark matter clump exists in the solar system's outskirts, It might explain the clustering of trans-Neptunian objects. Its gravitational pull could mimic the effects of a massive planet, influencing the orbits of distant bodies. The idea of a primordial black hole has also been proposed as an alternative explanation. These hypothetical black holes, formed in the early universe, could have masses similar to Planet 9 but would be far smaller in size. A primordial black hole the size of a grapefruit could exert the same gravitational influence as a planet. However, its lack of light or heat emission makes it nearly impossible to detect through traditional observation methods. If such a black hole exists, it might be surrounded by a halo of dark matter or other particles. This halo could produce faint signals, such as gamma rays, which might be detectable with specialized instruments. The possibility of dark matter or a primordial black hole challenges conventional theories about the solar system. It introduces entirely new factors that could reshape our understanding of gravity and celestial dynamics. However, these explanations remain speculative. Dark matter and primordial black holes have not been observed directly in the outer solar system, and their presence here would require unusual conditions. Detecting a primordial black hole would require instruments capable of capturing indirect effects, such as gravitational lensing. This phenomenon, where light bends around a massive object, could provide evidence of its existence. Dark matter, on the other hand, interacts primarily through gravity, making it even harder to study. Its presence could only be inferred from the behavior of other objects in its vicinity, leaving much to interpretation. One challenge with these theories is that they do not fully align with the predictions of Planet 9's orbit. The observed patterns in the Kuiper belt are more consistent with the influence of a single, massive planet. Despite their limitations, these ideas push the boundaries of traditional astronomy. They force scientists to consider possibilities that extend beyond the familiar realm of planets and into the unknown territory of exotic matter. Future research may help determine whether dark matter, a primordial black hole, or a combination of factors is at play. For now, these ideas remain intriguing possibilities that add depth to the mystery of the outer solar system. Re-evaluating observational data is a critical step in the search for Planet 9. Astronomers continuously revisit older surveys to see if faint signals of the planet were overlooked or misclassified. Many datasets were collected before the concept of Planet 9 was even proposed. These archives may contain subtle clues, but identifying them requires advanced processing techniques and updated search algorithms. Improvements in image analysis have allowed researchers to reprocess existing data with greater precision. Faint objects that were previously dismissed as noise are now being scrutinized for signs of Planet 9. One focus is on slow-moving objects that might have been missed in earlier searches. Planet 9's vast distance means it would move very slowly across the sky, blending in with the background stars. By comparing observations taken years or even decades apart, astronomers can identify faint objects that exhibit motion consistent with a distant planet. This method has proven effective for detecting trans-Neptunian objects. Some surveys originally aimed at different targets may have captured parts of Planet 9's orbit by chance. Reviewing this data for faint moving points could provide new leads in the ongoing search. Re-evaluation also includes examining the paths of known trans-Neptunian objects. Any small discrepancies in their orbits might point to gravitational interactions with an unseen planet. Data from infrared telescopes, which are more sensitive to cold, distant objects, is being revisited with updated models. These models can better predict the faint thermal signature that Planet 9 might emit. Older studies that discounted the presence of a ninth planet are being re-examined in light of new evidence. Advances in technology and techniques may uncover details that were missed at the time. The process also involves cross-referencing multiple datasets. Combining information from different observatories increases the chances of spotting a faint object that might have gone unnoticed in a single survey. Each re-evaluation brings the potential for new discoveries, but also introduces challenges. The sheer volume of data and the faintness of Planet 9's expected signal require extraordinary attention to detail. As technology continues to improve, the value of these older datasets grows. What was once unrecognizable noise may hold the key to solving the mystery of Planet 9's existence. The search for Planet 9 has profound implications for how we understand the Kuiper belt. Its existence could explain the unusual clustering of orbits among the distant objects in this icy region, shedding light on the forces that shape it. The Kuiper belt was once thought to be a relatively uniform collection of small, icy bodies. However, the discovery of complex orbital patterns suggests that powerful gravitational forces have played a role in its evolution. If Planet 9 exists, its influence over billions of years could have sculpted the distribution of objects in the Kuiper belt. This would help explain why some regions are densely populated, while others are mysteriously sparse. The gravitational pull of planet the 9th of May also account for the high eccentricities of certain Kuiper belt objects. These stretched-out orbits suggest interactions with a massive body far beyond Neptune. Another implication is the presence of detached objects, which are no longer influenced by Neptune's gravity. Planet 9's force could explain how these objects were pushed into such isolated orbits. The Kuiper belt is also home to unusual orbital resonances, where objects move in synchronized patterns. Planet 9 could be the hidden force maintaining these resonances, creating stability in the outer solar system. Its presence may reveal why certain objects are tilted at extreme angles relative to the plane of the solar system. These inclinations suggest a long-term influence that only a massive, distant planet could exert. The study of the Kuiper belt has already revealed surprises, such as the discovery of large dwarf planets like Eris and Haumea. Planet 9's discovery would continue this trend, highlighting the complexity and dynamism of this distant region. Planet 9 could also offer insights into how the Kuiper belt formed. Its migration or capture might have scattered smaller objects, leaving behind the structure we observe today. If the planet is found, it could redefine what we consider the boundaries of the Kuiper belt. Its influence may extend much farther than previously thought, challenging our understanding of the solar system's outer edge. The presence of a massive planet would also prompt a re-evaluation of existing models of solar system formation. It suggests that the Kuiper belt is not just a static remnant of the early solar system, but an evolving region shaped by dynamic forces. Ultimately, Planet 9 would provide a unifying explanation for many of the Kuiper belt's anomalies. Its discovery could transform our understanding of this distant region, revealing it to be a more intricate and interconnected part of the solar system than ever imagined. Alternative theories present significant challenges to the Planet 9 hypothesis by offering different explanations for the observed anomalies in the outer solar system. These theories question whether a single massive planet is truly necessary to account for the clustering of distant objects. One prominent idea is that the clustering could result from observational biases. Telescopes tend to focus on certain regions of the sky, potentially creating the illusion of patterns that aren't representative of the whole Kuiper belt. Another alternative involves a dense disk of smaller objects spread across the outer solar system. The combined gravitational influence of these icy bodies could mimic the effects attributed to Planet 9, shaping the orbits of trans-Neptunian objects. Some researchers argue that early interactions with a passing star might have disrupted the orbits of outer solar system bodies. This scenario could explain the observed clustering without requiring the presence of a hidden planet. Primordial black holes are another possibility. Although highly speculative, a black hole with the mass of Planet 9 could produce similar gravitational effects, while being completely undetectable in visible light. Dark matter offers yet another challenge to the Planet 9 theory. If a clump of dark matter exists in the solar system's outskirts, it could explain the gravitational anomalies without involving a traditional planet. Chaotic dynamics within the solar system itself may also play a role. Some scientists suggest that the observed orbital patterns could arise naturally from interactions among the known planets and Kuiper belt objects over billions of years. Statistical arguments have been made against the significance of the clustering. Some studies suggest that the patterns could be coincidental, the result of random orbital distributions rather than the influence of an unseen object. Planetary migration theories present another challenge. If Neptune or Uranus migrated outward during the early solar system, their movements alone might have shaped the current structure of the Kuiper belt. Alternative theories also question the stability of a Planet 9-like orbit. Critics argue that a planet with such a distant, elongated path would likely have been ejected from the solar system entirely over time. The difficulty in directly detecting Planet 9 further supports these challenges. Without observational evidence, skeptics argue that it's more plausible to explore other explanations for the gravitational anomalies. These alternative theories not only test the strength of the Planet 9 hypothesis, but also push astronomers to refine their models. Whether Planet 9 exists or not, these challenges ensure that every possibility is thoroughly examined. Planet 9's gravitational influence, though subtle, could extend to the outer planets, particularly Neptune and Uranus. Over long timescales, its presence might cause slight shifts in their orbits, altering their positions relative to the Sun. These changes would likely be too small to detect directly, but could accumulate over billions of years. Such subtle effects might help explain certain irregularities observed in the motions of the outer planets. One possibility is that Planet 9 has affected Neptune's orbit, causing it to migrate outward during the solar system's early history. This outward movement could have disrupted smaller objects and shaped the Kuiper belt's structure. Its influence may also extend to Uranus, contributing to the slight tilt of its rotation axis. While this tilt is often attributed to a massive collision, the presence of a distant planet could provide an alternative explanation. Planet 9's gravity might create resonances that impact the motion of the gas giants. These resonances could lock certain orbits into specific patterns, maintaining stability in the outer solar system. Another effect could be the redistribution of material in the Kuiper belt. By influencing how objects interact with Neptune and Uranus, Planet the 9th of May have helped create the gaps and clusters seen in this distant region. Interactions with Planet 9 might also affect how comets and other small bodies are scattered toward the inner solar system. The gravitational pull of the outer planets could amplify these effects, altering their trajectories. The presence of such a massive object might explain some discrepancies in the solar system's angular momentum. The outer planets' combined movements could reflect the hidden influence of Planet 9. Its gravitational reach, though faint, might extend inward during certain phases of its orbit. These periodic interactions could leave subtle imprints on the dynamics of Neptune, Uranus, and possibly even Saturn. Planet 9's long orbit might also impact the orbital eccentricities of the outer planets over time. These gradual changes could contribute to variations in their distances from the Sun, creating detectable patterns. If Planet 9 played a role in the early solar system's evolution, it might have helped guide the formation and migration of the outer planets. Its influence could have been stronger in the past, shaping their initial paths. Even if its effects on the outer planets are minimal today, studying their motions could provide indirect evidence of Planet 9's existence. Small deviations from predicted models might point to the gravitational presence of this elusive world. Planet 9's gravitational pull could significantly influence the trajectories of comets in the outer solar system. Its presence might redirect some comets from the distant Oort cloud or Kuiper belt, sending them on paths toward the inner solar system. By altering the orbits of these icy bodies, Planet 9 could contribute to the frequency of long-period comets that pass near the Sun. These changes might explain certain patterns in cometary arrivals observed over centuries. As comets approach the region dominated by Planet 9's gravity, their orbits could become destabilized. This destabilization might eject some comets entirely from the solar system, while drawing others closer to the Sun. Its influence could also account for the highly eccentric orbits seen in some long-period comets. These extreme trajectories suggest interactions with a massive body far beyond the known planets. Planet 9 might act as a gravitational gatekeeper, filtering which comets can enter the inner solar system. By nudging objects into resonances or scattering them outward, it shapes the overall population of active comets. The planet's elongated orbit likely plays a role in these effects. As Planet 9 moves through its distant path, it could periodically encounter clusters of comets, altering their distribution and direction. Comet showers, events where multiple comets approach the inner solar system over a short period, might also be linked to Planet 9. Its gravitational interactions could trigger these events, bringing comets into the Sun's vicinity. Some theories suggest that Planet 9 could contribute to the origins of interstellar objects like Oumuamua. Its interactions might eject comets or asteroids into trajectories that leave the solar system entirely. By influencing the orbits of smaller bodies, Planet 9 might also affect the overall composition of the Oort cloud. Over time, its gravitational reach could reshape the cloud's boundaries, redistributing material throughout the outer solar system. The planet's impact on comets could have broader implications for Earth. Periodic increases in comet activity might correlate with historical extinction events or changes in Earth's climate, providing a potential link between Planet 9 and life on Earth. Planet 9's gravitational effects could also aid in discovering new comets. By tracking unusual trajectories or identifying objects with extreme orbits, astronomers might uncover evidence of its influence. Studying how Planet 9 affects cometary dynamics helps refine our understanding of the solar system's structure. These interactions highlight the interconnected nature of celestial bodies, revealing how even distant forces can shape the paths of comets. The potential existence of Planet 9 forces astronomers to reconsider traditional models of the solar system. For centuries, these models have focused on the 8 known planets, but the inclusion of a distant 9th planet could rewrite our understanding of its structure. One of the most significant changes involves the boundaries of the solar system. If Planet 9 is real, its orbit would extend the solar system's reach far beyond the current edge defined by Neptune. Models of planetary formation would also need to be revised. Planet 9's size and distance suggest that either it formed in an unexpected region or it was ejected from a closer orbit early in the solar system's history. The planet's presence might also impact theories of planetary migration. If it was pushed outward by gravitational interactions, it could provide new insights into how giant planets like Jupiter and Saturn shape the solar system. Another area of change involves the distribution of smaller bodies. The gravitational influence of Planet 9 could explain the clustering of trans-Neptunian objects, requiring models to account for these patterns. Its effects on the Kuiper belt challenge assumptions about this region being a relatively stable remnant of the early solar system. Instead, it suggests an evolving, dynamic structure, influenced by unseen forces. The discovery of Planet 9 would also refine our understanding of orbital resonances. Its gravitational pull could create new resonances, stabilizing or destabilizing the orbits of smaller objects over time. Including Planet 9 in solar system models might resolve long-standing mysteries, such as the unexpected tilt of the Sun's axis relative to the orbital plane. Its mass and distant orbit could account for this misalignment. The potential interactions between Planet 9 and the Oort cloud would further expand these models. Its gravity might play a role in shaping the distribution and behavior of the icy bodies that populate this distant region. Comet dynamics would also be re-evaluated. Models would need to consider how Planet 9 redirects or scatters comets, influencing the rate and timing of their arrivals in the inner solar system. The inclusion of a 9th planet aligns the solar system more closely with what is observed in other star systems. Many exoplanetary systems contain super-Earths or distant giant planets, suggesting that Planet 9 could fill a missing piece in our own system. Revising these models allows for a deeper understanding of the forces that govern the solar system. The potential discovery of Planet 9 would provide a new framework for exploring the origins and evolution of our cosmic neighborhood. Some scientists speculate that Planet 9 could have an indirect connection to Earth's historical extinction events. Its gravitational influence on comets and other celestial bodies might periodically increase the number of impacts on Earth. As Planet 9 moves through its elongated orbit, it could disturb objects in the Oort cloud or Kuiper belt. These disturbances might send a cascade of comets toward the inner solar system, increasing the likelihood of collisions with Earth. Evidence from Earth's geological record shows periodic spikes in impact craters and extinction events. Planet 9's orbit might align with these patterns, suggesting it plays a role in triggering these catastrophic events. The idea is that Planet 9 could act as a gravitational trigger, destabilizing distant icy bodies at regular intervals. These objects, drawn toward the Sun, could become long-period comets that pose a threat to life on Earth. One theory links these events to the planet's aphelion and perihelion points. When Planet 9 reaches certain positions in its orbit, its gravitational influence on distant objects might be strongest, leading to increased comet activity. Some extinction events, such as the one that ended the dinosaurs, have been linked to massive impacts. If Planet 9 contributes to these patterns, it could offer a new perspective on the causes of mass extinctions. The timing of these events remains uncertain, but models of Planet 9's orbit suggest it could create cycles of increased comet activity. These cycles might align with periods of heightened extinction risk on Earth. By sending new comets into the inner solar system, Planet 9 could also contribute to the creation of meteor showers. These events might leave lasting geological and atmospheric signatures, influencing Earth's environment. Some researchers propose that Planet 9's role extends beyond direct impacts. The increased comet activity it triggers could also lead to atmospheric changes, altering Earth's climate over long timescales. If confirmed, This connection would highlight the far-reaching effects of celestial dynamics on Earth. Planet Nine's distant orbit might seem remote, but its gravitational influence could have profound implications for life on our planet. Testing this hypothesis would require precise models of Planet Nine's orbit and its interactions with other celestial bodies. Comparing these models to Earth's impact history could reveal correlations that strengthen the theory. Whether or not Planet Nine has directly influenced extinction events, its discovery would provide new insights into the relationship between the solar system's outer regions and the history of life on Earth. Planet Nine's gravitational influence could lead to gradual orbital shifts throughout the solar system over long timescales. These changes might be subtle but could accumulate, altering the positions and movements of other celestial bodies. One prediction is that Planet Nine could induce slight tilts in the orbits of the outer planets. Over millions of years, these shifts might affect the alignment of Neptune, Uranus, and even the Kuiper belt. Its presence may also cause variations in the eccentricities of certain orbits. Objects in resonance with Planet Nine could experience changes in how elongated their paths become, reshaping their trajectories. Planet Nine's own orbit might shift due to gravitational interactions with the known planets. These interactions could result in its orbit becoming even more tilted or eccentric over billions of years. The distribution of trans-Neptunian objects is also likely to change under Planet Nine's influence. Some objects might be pulled into new resonances, while others could be ejected from the solar system entirely. As new objects interact with Planet Nine's gravity, their orbits could stabilize into patterns that reflect the planet's long-term influence. These shifts would provide clues about its mass and orbital path. Its interactions might extend to the Oort cloud, where its gravity could trigger slow, widespread shifts in the orbits of icy bodies. These movements could contribute to periodic bursts of comet activity closer to the Sun. Simulations suggest that Planet Nine could also affect the orbital inclination of smaller bodies. These shifts might align certain objects with the planet's tilted path, revealing a distinct orbital signature. If Planet Nine migrates over time, its gravitational reach could expand or contract, altering the dynamics of the outer solar system. This migration might explain historical changes in the structure of distant regions like the Kuiper belt. Long-term shifts in Planet Nine's orbit could also influence the solar system's overall angular momentum. Its presence might subtly alter the rotational dynamics of the system, impacting how energy is distributed across celestial bodies. These orbital shifts could provide a roadmap for discovering Planet Nine's location. Tracking the changes in other objects might reveal patterns that point directly to the planet's gravitational effects. Understanding these future shifts would not only refine the search for Planet Nine, but also expand our knowledge of how distant forces shape the evolution of the solar system over time. Ground-based telescope surveys play a critical role in the search for Planet Nine. These surveys are designed to scan vast regions of the sky, capturing faint objects that might otherwise go unnoticed. Large telescopes with wide-field capabilities are particularly useful for this task. They can cover significant portions of the sky in a single observation, increasing the chances of detecting distant celestial bodies. One of the key challenges for ground-based surveys is filtering out noise from background stars and galaxies. Advanced image processing techniques help astronomers identify moving objects that could be potential candidates for Planet Nine. Repeated observations are essential for confirming the motion of faint objects. By comparing images taken over weeks or months, astronomers can track the slow movement of distant objects against the fixed background of stars. Surveys like the Dark Energy Survey and Pan-STARRS have already contributed valuable data. Although these projects were not specifically designed to find Planet Nine, their observations of the outer solar system have revealed new trans-Neptunian objects. The Vera C. Rubin Observatory, once operational, is expected to revolutionize the search. With its powerful camera and wide field of view, it will provide unprecedented coverage of the night sky, ideal for detecting faint, slow-moving objects like Planet Nine. Even smaller observatories contribute by focusing on specific regions of the sky. These targeted efforts complement larger surveys, filling in gaps and refining the search area based on theoretical predictions. Ground-based telescopes face limitations, including atmospheric distortion and light pollution. Adaptive optics systems and remote high-altitude locations help mitigate these issues, improving image clarity and sensitivity. Some surveys prioritize infrared observations, which are better suited for detecting cold, distant objects. Infrared telescopes on the ground use specialized instruments to capture the faint heat emissions that Planet 9 might produce. International collaboration is key to maximizing the effectiveness of these surveys. By coordinating efforts, astronomers around the world can continuously monitor potential regions where Planet 9 might be located. The data collected by ground-based telescopes is often reanalyzed as search methods improve. Older surveys are revisited with updated algorithms, sometimes revealing faint objects that were previously overlooked. Ground-based telescope surveys provide the foundation for the search, generating the data that guides more focused efforts. Their contributions are vital in narrowing down the possibilities and bringing us closer to uncovering Planet 9. Space-based observatories offer a unique advantage in the search for Planet 9. Operating above Earth's atmosphere, they avoid the distortions and light pollution that can hinder ground-based telescopes. These observatories are particularly well suited for detecting faint, distant objects. Their ability to capture clearer, sharper images increases the likelihood of spotting Planet 9's subtle signals in the vastness of space. Infrared space telescopes like the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer have been instrumental in surveying the outer solar system. Their sensitivity to heat emissions allows them to detect cold, distant objects that reflect little sunlight. The James Webb Space Telescope is expected to contribute significantly to this effort. With its advanced infrared capabilities, it can capture even the faintest thermal radiation, providing a powerful tool for locating Planet 9. Space-based missions also benefit from continuous observation. Unlike ground-based telescopes, which are affected by weather and daylight, space observatories can monitor target regions uninterrupted for extended periods. The Gaia mission, though focused on mapping stars in the Milky Way, has provided valuable data for the Planet 9 search. By tracking precise motions of stars and distant objects, it helps refine predictions about the planet's location. Future missions could be specifically designed to search for Planet 9. A dedicated space telescope with a wide field of view and enhanced infrared sensitivity would be ideal for exploring the faint edges of the solar system. Space observatories also allow for multi-wavelength observations. Combining optical, infrared, and other data streams provides a more complete picture, improving the chances of detecting a faint object like Planet 9. Collaborations between space missions and ground-based surveys enhance the search. Data from space observatories can guide ground-based efforts, while follow-up observations from Earth help confirm potential detections. The vastness of the search area remains a challenge, even for space-based telescopes. Missions must prioritize specific regions based on theoretical models and gravitational clues provided by trans-Neptunian objects. Space-based missions also face limitations, such as finite operational lifespans and the need for precise calibration. However, their ability to operate in an environment free from atmospheric interference makes them indispensable in the search for Planet 9. With advances in technology and new missions on the horizon, space-based observatories are poised to play a central role in solving the mystery of Planet 9. Their contributions bring us closer to uncovering this hidden world in the outer solar system. Infrared detection techniques are crucial for identifying distant objects like Planet 9. Unlike visible light, infrared radiation reveals the heat emitted by cold bodies in the far reaches of the solar system. Planet 9's low temperature makes it nearly invisible in optical wavelengths, but its faint thermal emissions could stand out in the infrared spectrum. Infrared telescopes are specifically designed to capture this type of faint signal. One advantage of infrared detection is its ability to see through interstellar dust. While dust can obscure visible light, infrared radiation can pass through, making it ideal for studying distant faint objects. Ground-based infrared observatories like the Subaru telescope have already contributed to the search. Their sensitive instruments help detect small amounts of heat radiating from objects far beyond Neptune. Space-based infrared telescopes, such as the Spitzer Space Telescope, operate without interference from Earth's atmosphere. This gives them a clearer view of the faint thermal signals emitted by cold, distant planets. The James Webb Space Telescope is expected to revolutionize infrared detection. Its unparalleled sensitivity will allow astronomers to search for Planet 9 with unprecedented precision, focusing on regions where thermal emissions are most likely. Infrared surveys require careful calibration to distinguish between genuine detections and background noise. Stars, galaxies, and other sources emit infrared radiation, creating challenges in identifying a faint object like Planet 9. Repeated observations are essential for confirming an infrared signal. By tracking an object's motion over time, astronomers can rule out other possibilities, such as distant stars or instrument artifacts. The effectiveness of infrared detection depends on the planet's composition. If Planet 9 has a surface covered in highly reflective ices, its heat emissions may be weaker, requiring even more sensitive instruments to detect. Infrared techniques also allow scientists to estimate a planet's temperature and size. By analyzing the intensity of its thermal radiation, astronomers can infer important details about its physical properties. Future missions dedicated to infrared astronomy, such as space-based telescopes designed for deep sky surveys, will enhance these efforts. With greater sensitivity and wider coverage, they could locate Planet 9 even in the faintest corners of the solar system. Infrared detection remains one of the most promising approaches for finding Planet 9. Its ability to capture the planet's faint heat signature provides a critical pathway for uncovering this elusive object. Citizen science has become an invaluable part of the search for Planet 9. By involving the public in analyzing astronomical data, researchers can tap into a vast network of observers and contributors. Projects like Backyard World's Planet 9 allow volunteers to sift through telescope images, searching for faint moving objects that could be distant planets or other trans-Neptunian bodies. This crowdsourced approach significantly increases the chances of spotting something unusual. Participants often examine infrared data, looking for signs of slow-moving objects against the static background of stars. This method has already led to the discovery of numerous brown dwarfs and other celestial objects. The sheer volume of data generated by modern telescopes is too large for astronomers to analyze alone. Citizen scientists help process these enormous datasets, identifying potential candidates that automated systems might overlook. By contributing their time and effort, volunteers provide an extra layer of scrutiny. Their keen eyes and collective effort can uncover subtle patterns that point to Planet 9's location. Citizen science also engages amateur astronomers with their own telescopes. These skilled observers often follow up on potential candidates, confirming whether an object shows the motion expected for a distant planet. Online platforms make it easy for participants to collaborate and share findings. Through these networks, discoveries are quickly verified and passed on to professional astronomers for further study. The diversity of perspectives among citizen scientists is a strength. People from all over the world bring unique skills and insights, often catching details that might go unnoticed in automated surveys. Involving the public also raises awareness and excitement about astronomy. The possibility of discovering Planet 9 inspires curiosity and fosters a deeper connection to the mysteries of the cosmos. Citizen science projects are supported by advanced tools and tutorials, enabling volunteers to contribute meaningfully, even without prior expertise. This accessibility ensures that anyone with an interest can take part in the search. These contributions complement the work of professional astronomers, providing valuable data and insights. Together, this collaboration bridges the gap between large-scale surveys and localized efforts to identify faint objects. As technology continues to advance, citizen scientists will play an even greater role in the search for Planet 9. Their dedication and enthusiasm add momentum to this ongoing quest, bringing us closer to solving one of astronomy's greatest mysteries. Future projects are poised to take the search for Planet 9 to the next level. New technologies and dedicated missions will focus on uncovering this elusive planet in the farthest reaches of our solar system. The Vera C. Rubin Observatory is one of the most anticipated projects. With its powerful wide-field telescope, it will scan the entire sky repeatedly, capturing detailed images that could reveal faint, distant objects like Planet 9. Space-based missions will also play a key role. Advanced infrared telescopes designed to operate outside Earth's atmosphere will have the sensitivity needed to detect the planet's faint thermal emissions. Dedicated surveys using next-generation instruments will prioritize regions of the sky where Planet 9 is most likely to be. These focused efforts will build on theoretical models and data from trans-Neptunian objects. International collaboration is central to these future projects. Observatories and space agencies around the world will combine their resources and expertise, increasing the likelihood of success. Artificial intelligence will enhance the efficiency of these searches. Machine learning algorithms will analyze massive datasets, identifying subtle patterns that might indicate Planet 9's presence. Follow-up missions could include smaller satellites equipped with specialized cameras. These compact instruments would focus exclusively on confirming potential detections and refining orbital predictions. Future infrared surveys, like the proposed SPHEREX mission, will provide a deeper look into the outer solar system. By mapping faint heat signatures, they could pinpoint areas where Planet 9's thermal radiation might emerge. High-altitude observatories, such as those using balloons or mountaintop facilities, will complement space-based efforts. These platforms avoid much of the atmospheric interference, providing clearer observations of distant regions. Some proposals involve designing telescopes specifically for Planet 9's detection. These instruments would prioritize wide coverage and extreme sensitivity, tailored to the unique challenges of locating such a distant object. Long-term missions might even include spacecraft sent to explore the outer solar system directly. Equipped with advanced sensors, these probes could gather detailed data on distant regions, offering new clues about Planet 9. As these projects come online, they will transform the search for Planet 9. Each step forward will refine our understanding of the solar system's outer boundaries, bringing this mysterious world closer to discovery. Planet 9 has captured the imagination of the public, sparking curiosity about the mysteries of the outer solar system. The idea of a hidden world lurking beyond Neptune feels like something straight out of science fiction. This fascination stems from the allure of the unknown. People are drawn to the possibility that there's still a major discovery waiting to be made in our own cosmic backyard. Media coverage and documentaries have amplified interest in the Planet 9 search. These stories highlight the scientific process, bringing complex astronomical concepts to a wider audience. The potential discovery of Planet 9 taps into a timeless human desire to explore. It reminds us that even with all our technological advances, there are still uncharted regions of the solar system. Social media has played a key role in fueling excitement. Updates from scientists and observatories are shared instantly, allowing enthusiasts to follow the search in real time. Planet 9 has also inspired creative interpretations in books, movies, and art. These depictions range from scientific representations to imaginative portrayals of what this distant planet might look like. Amateur astronomers are particularly captivated by the idea of contributing to its discovery. Citizen science projects have made it possible for anyone with a computer to join the search, turning fascination into action. The mystery of Planet 9 resonates with people of all ages. For younger generations, it serves as an entry point into the wonders of astronomy, inspiring a new wave of interest in science. Its connection to the unknown raises philosophical questions. The search for Planet 9 forces us to consider what else might be hidden in the vastness of space, far beyond our current understanding. This excitement isn't limited to professionals or enthusiasts. Planet 9 has become a topic of casual conversation, drawing interest from those who may not typically follow scientific developments. The possibility of finding Planet 9 reminds us that science is a journey. The public fascination with this hidden world reflects a shared curiosity about the universe and our place within it. As the search continues, the story of Planet 9 brings people together, uniting us in the quest to uncover one of the solar system's most enduring mysteries. Discoveries like Planet 9 challenge our understanding of the solar system and expand the boundaries of what we know about the universe. Every new finding forces us to rethink established models and consider possibilities that were once thought to be purely speculative. The search for distant objects in the solar system reshapes our view of space itself. It reminds us that there is still much to explore within our own neighborhood, far beyond the known planets. Planet 9's potential existence pushes the limits of current technology. The need to detect such a faint object encourages advancements in telescope design, imaging techniques, and computational methods, all of which benefit astronomy as a whole. These discoveries encourage us to look beyond our immediate surroundings and consider the vastness of the universe. They suggest that our solar system might be just one example of a much larger cosmic landscape filled with unknown worlds. Each new discovery about the outer solar system adds a layer to our understanding of planetary formation. The existence of a ninth planet, if proven, could offer insights into how planets form and evolve in the farthest reaches of a star's gravitational influence. Findings like this help connect the dots between what we know about exoplanets and our own solar system. As we discover new planets orbiting distant stars, Planet 9 could serve as a bridge, showing how similar processes might have shaped our own cosmic neighborhood. The idea of a hidden planet influences our understanding of gravitational forces. It suggests that even objects far beyond Neptune can shape the orbits of smaller bodies, revealing how interconnected the solar system is. By studying the search for Planet 9, we begin to appreciate how little we still understand about the universe. Each discovery highlights gaps in our knowledge, pushing scientists to ask deeper questions about the nature of space and time. These revelations often stir the curiosity of the public, drawing more people into the world of science. As people become more aware of discoveries like Planet 9, it sparks a greater interest in space exploration and the fundamental mysteries of our existence. The quest for Planet 9 is a perfect example of how science evolves. What once seemed impossible or fantastical is now being actively investigated, showing how our understanding of the universe is constantly shifting. These discoveries highlight the vastness of space, reminding us that there is always more to learn. Every new finding, like the search for Planet 9, expands our knowledge and reshapes our perception of the cosmos. Ultimately, discoveries like Planet 9 help put our place in the universe into perspective. They remind us that we are part of something far larger, a dynamic and ever-evolving cosmos that is still full of mysteries waiting to be uncovered. The search for Planet 9 has sparked intense scientific debates, with researchers offering competing theories to explain the evidence. Some argue that the gravitational anomalies are best explained by a hidden planet, while others suggest alternative explanations, such as dark matter or the influence of smaller bodies. These debates foster collaboration among scientists from different disciplines. Astronomers, mathematicians, and physicists come together, each bringing their expertise to the table to tackle the puzzle of Planet 9's existence. Mathematical models and simulations play a key role in these discussions. Some researchers focus on refining these models to account for the observed orbital patterns, while others challenge the assumptions behind the calculations. The process of scientific debate is essential in refining theories and eliminating less likely explanations. By testing each hypothesis against observed data, scientists work to narrow down the most plausible scenarios for Planet 9. The existence of Planet 9 could also reshape our understanding of the solar system's formation. If the planet's orbit and influence are confirmed, it would challenge existing models and require new theories to explain how it fits into the solar system's architecture. The search for Planet 9 has led to greater cooperation between observatories around the world. Different research teams share their findings, using a collaborative approach to gather and analyze data that could confirm or disprove the planet's existence. The role of citizen science in this debate cannot be underestimated. By involving the public in analyzing astronomical data, researchers are able to expand the scope of the search and bring new perspectives to the discussion. Collaboration extends beyond just the sharing of data. Researchers also work together on designing new technologies and methods, ensuring that future telescope surveys and space missions are optimized to find Planet 9. As new discoveries are made, the debate continues to evolve. Each piece of evidence adds a new layer to the conversation, prompting scientists to refine their models and explore new possibilities. The dynamic nature of these scientific debates ensures that the search for Planet 9 remains at the forefront of astronomical research. As new instruments and techniques become available, the discussion about the planet's existence will continue to evolve. Through rigorous analysis and open collaboration, the scientific community works towards resolving the mystery of Planet 9. This ongoing dialogue demonstrates how the pursuit of knowledge is a collective effort, driven by curiosity and the desire to understand our place in the universe. The debates surrounding Planet 9 are a testament to the collaborative nature of science. By challenging assumptions and testing new ideas, researchers move closer to understanding the true nature of our solar system. The mystery surrounding Planet 9 serves as a powerful inspiration for future astronomers. The idea that there could be a hidden planet waiting to be discovered fuels the curiosity of young students and aspiring scientists. As they follow the search for Planet 9, future astronomers are introduced to the challenges and excitement of space exploration. The process of finding a faint, distant object teaches them about the perseverance required in scientific discovery. Planet 9's search also highlights the importance of collaboration. Aspiring astronomers see how scientists around the world share data and work together, reinforcing the idea that scientific progress is often a collective effort. The advancements in technology needed to locate Planet 9 also inspire innovation in the field of astronomy. New telescopes, algorithms, and imaging techniques are developed, showing the next generation of scientists how they can shape the future of the field. The ongoing efforts to find Planet 9 demonstrate the evolving nature of astronomy. Aspiring scientists learn that new discoveries often come from rethinking old ideas and pushing the boundaries of current knowledge. The excitement of finding a new planet, especially one so far from the Sun, encourages young astronomers to dream big. Planet 9 serves as a symbol of the untapped mysteries waiting to be explored in the vastness of space. For those interested in technology, the search for Planet 9 is a prime example of how computational science intersects with traditional astronomy. Students see how data analysis and simulations play a crucial role in modern scientific exploration. The debate surrounding Planet 9 also teaches future astronomers about the importance of skepticism and critical thinking. In science, ideas must be rigorously tested, and only through careful evaluation can new theories gain acceptance. Planet 9's potential discovery sparks a sense of wonder and excitement that drives young people toward careers in science. The mystery challenges them to look beyond Earth and explore the depths of space for answers. By watching current researchers tackle one of astronomy's most pressing questions, students are encouraged to embark on their own scientific journeys. They see firsthand how determination and creativity lead to progress in the search for knowledge. The story of Planet 9 serves as a reminder that the universe is full of unanswered questions. This inspires future astronomers to continue the search, knowing that each discovery could unlock new mysteries about the cosmos. Through the search for Planet 9, future generations of astronomers are encouraged to think critically, innovate, and pursue their passion for exploration. The journey to uncovering this distant planet is just one chapter in the broader story of space exploration. The search for Planet 9 draws intriguing parallels to the discovery of exoplanets or planets orbiting stars outside our solar system. Both types of planets challenge our understanding of planetary formation and the architecture of solar systems. Like many exoplanets, Planet 9's distant orbit makes it difficult to detect directly. Its faint presence in the outer solar system mirrors how distant exoplanets are often hidden by their faint light, requiring sensitive instruments to identify them. The idea of a super-Earth with a mass roughly 10 times that of Earth is another common thread between Planet 9 and exoplanets. This category of planets has become a significant focus of exoplanet research, with astronomers studying their characteristics to learn more about planetary formation. Planet 9's predicted orbit far beyond Neptune is similar to the orbits of some exoplanets discovered around distant stars. These planets often have eccentric, elongated orbits, just as Planet 9 is theorized to have. The challenges in finding Planet 9 are akin to the difficulties astronomers face when searching for exoplanets. Detecting such faint objects, whether they are distant planets in our own solar system or far-off worlds orbiting other stars, requires cutting-edge technology and innovative techniques. Much like the discovery of exoplanets revolutionized our understanding of planetary systems, the search for Planet 9 could redefine our view of the solar system. It raises questions about the diversity of planetary types and the potential for other hidden worlds waiting to be discovered. Both Planet 9 and exoplanets push the boundaries of observational astronomy. The methods used to detect these objects, ranging from gravitational influence to the detection of faint signals, highlight the ongoing advancements in telescope technology. The possibility of Planet 9 suggests that our own solar system may have more in common with other distant star systems than we previously thought. The presence of another large planet in our system mirrors the discovery of similarly large exoplanets in far-off systems. Exoplanet research has broadened our understanding of planetary systems beyond our own. In a similar way, the search for Planet 9 could offer new insights into how our own solar system formed and how it compares to systems in other parts of the galaxy. Planet 9's potential to explain anomalies in the outer solar system resembles how exoplanet discoveries have reshaped models of stellar evolution and planetary systems. Both highlight the complexity and unexpected nature of how planets interact with their environments. The study of exoplanets has expanded our understanding of planet formation across a variety of environments, from gas giants to rocky planets. Similarly, the discovery of Planet 9 could provide crucial clues about the forces at play in the outer solar system. Just as the search for exoplanets is a global endeavor, so too is the quest for Planet 9. Collaborations across observatories and countries demonstrate the collective effort needed to unlock the secrets of distant worlds, whether in our solar system or beyond. The search for Planet 9 could have implications beyond its own discovery, particularly in the context of habitable zones. Traditionally, the habitable zone around a star is defined by the distance where liquid water could exist on a planet's surface, but this definition is evolving. The discovery of exoplanets in the habitable zone of distant stars has already broadened our understanding of where life might exist. If Planet 9 or another distant planet is found to support an atmosphere or subsurface oceans, it could expand these criteria even further. Planet 9, being far from the Sun, would not fall within the traditional habitable zone. However, it could still harbor the conditions necessary for life, such as the possibility of a subsurface ocean heated by internal processes. This challenges our current assumptions about habitability. In some cases, moons of distant planets, or even objects like Planet 9, could provide the right conditions for life, even if they are far beyond the traditional habitable zone. Astronomers are beginning to consider a wider range of factors that could support life beyond just distance from a star. The presence of geothermal energy, tidal heating and subsurface water may make distant planets and moons more hospitable than previously thought. Planet 9's potential discovery would encourage scientists to rethink the boundaries of the habitable zone. This could lead to broader criteria for what makes a planet or moon capable of supporting life. The concept of a habitable zone has traditionally focused on planets orbiting stars, but the search for distant objects like Planet 9 suggests we should consider planets or moons in a broader context. Even in the farthest reaches of the solar system, the right conditions might exist for life to thrive. If Planet 9 has an atmosphere or a stable internal environment, it could challenge current models of habitability, particularly in relation to distant low-light worlds. Such discoveries would push the boundaries of what we consider livable space. The idea of habitability is evolving to include more extreme environments. Moons of gas giants like Jupiter and Saturn, or planets in distant orbits like Planet 9, could hold valuable lessons about life in the most unexpected places. Planet 9's existence might spur the development of new models for detecting habitable conditions on planets that are not in the traditional habitable zone. These models would focus on the potential for life in environments where energy sources are not solely derived from sunlight. The idea of life existing in regions far from their star is becoming more plausible. Whether it's a subsurface ocean on a distant planet or life relying on geothermal energy, expanding the criteria for habitable zones opens new doors for astrobiology. The search for distant planets like Planet 9 could help redefine the search for extraterrestrial life. By broadening the criteria for what makes a world capable of sustaining life, we begin to realize that the universe may be full of surprises waiting to be discovered. The discovery of Planet 9 could bridge the gap between our solar system and the countless others discovered in the galaxy. By uncovering a hidden planet in the outer reaches, it would show that our solar system may not be as unique as once thought. The presence of a distant massive planet in our own system would mirror findings in exoplanetary systems. Many of these systems have revealed super-Earths and giant planets in far-flung orbits, similar to what we hypothesize for Planet 9. Understanding Planet 9 would provide insights into how planets form in distant regions, contributing to the growing field of comparative planetology. This could help us understand the formation and evolution of planetary systems across the galaxy. The way Planet 9 influences the outer solar system could offer clues about the gravitational dynamics in other star systems. Its effect on Kuiper belt objects may be similar to how distant planets shape the orbits of smaller bodies in other systems. The search for Planet 9 could lead to a better understanding of how planetary systems evolve over time. Just as we've discovered that planets in other systems can migrate, Planet 9's existence may reflect similar processes in our own solar system. Planet 9's potential discovery would highlight the similarities between our solar system and distant systems. It could show that planetary systems with large outer planets are more common than previously believed. Research into Planet 9 might also inform our understanding of planetary habitability in other systems. If distant planets like Planet 9 can host environments conducive to life, it may open up new possibilities for finding habitable planets in the galaxy. The quest for Planet 9 helps us place our solar system within a broader context. Each new discovery we make about the outer solar system brings us closer to understanding how our system fits into the larger structure of the universe. The search for this distant planet also drives technological advancements that could benefit the study of other star systems. Instruments designed to detect faint, far-off objects in our own system could also be used to observe exoplanets in distant stars. By studying the potential existence of Planet 9, scientists are developing tools that can be applied to the study of exoplanets. These advancements help bridge the gap between what we know about our solar system and what we can learn about distant systems. The concept of finding a planet in the far reaches of our own solar system challenges our preconceptions. If Planet 9 exists, it may provide a better understanding of how planets can exist in cold, distant regions, just like the farthest planets discovered in other systems. Ultimately, the search for Planet 9 connects our exploration of the solar system with the broader study of planetary systems throughout the universe. It serves as a reminder that the universe is interconnected, with each new discovery building on the last. The potential discovery of Planet 9 offers valuable insights into the processes of planetary formation and migration. Its existence could help explain how planets evolve and move over time, particularly in the outer regions of the solar system. Planet 9's orbit, if confirmed, suggests that planets can form much farther from their stars than we traditionally thought. It might have originally formed closer to the Sun and migrated outward, offering a glimpse into the early dynamics of our solar system. The gravitational influence of Planet 9 could also help explain how other distant objects in the Kuiper belt were shaped. Understanding its effect on the orbits of these objects could provide clues about the forces at work during the solar system's early years. The idea that planet the 9th of May have migrated over time is consistent with what we know about planetary systems in other star systems. Many exoplanets have been found in highly eccentric orbits, suggesting that planetary migration is a common feature of planetary system formation. Planet 9's position could also provide clues about the solar system's formation history. If it migrated outward, it would support the theory that gravitational interactions between planets and smaller bodies played a crucial role in shaping the structure of the solar system. The search for Planet 9 deepens our understanding of how planets interact with each other. Its gravitational pull could help explain the gaps and clustering observed in the outer solar system, revealing how planets influence the orbits of smaller bodies over time. Looking at Planet 9's potential location and orbit provides a broader perspective on how planets might form in isolation or in crowded environments. Its discovery would suggest that planets in distant orbits may be more common than previously believed, expanding our definition of where planets can form. If Planet 9's migration is confirmed, it could lead to a rethinking of how planetary systems develop. It would indicate that planetary migration is a significant factor in shaping the final configuration of solar systems, both in our own and beyond. The planet's large mass and remote orbit also provide insights into how massive planets may interact with smaller bodies, such as asteroids and comets. These interactions are essential in understanding how planetary systems evolve over long timescales. By studying Planet 9, astronomers can gain new perspectives on how planets migrate through their systems. This knowledge could help us understand the diversity of planetary systems observed in exoplanet surveys, and how our own solar system fits into this broader picture. The search for Planet 9 also raises questions about the early solar system's architecture. Its presence might suggest that the outer regions of the solar system were more dynamic and complex during its formation, possibly shaping the orbits of other planets as well. Examining Planet 9 could provide key evidence for understanding how planetary systems grow and evolve. The forces that shaped our solar system may also be at work in other systems, and uncovering them in our own system brings us closer to understanding these universal processes. The search for Planet 9 also ties into the broader quest to understand the potential for life elsewhere in the universe. If the planet exists and has the right conditions, it could provide insights into how life might emerge in extreme environments. Understanding the formation and dynamics of planets like Planet 9 expands our knowledge of where life could potentially thrive. The possibility of subsurface oceans or geologically active environments on distant planets could open up new pathways for life to form. The discovery of a planet far beyond Neptune encourages scientists to consider new environments where life could exist. By broadening our understanding of planetary systems, we can explore how life might arise on planets in colder, more distant parts of their solar systems. Planet Nine's potential to harbour life challenges our assumptions about the habitable zone. If it has the right conditions, it suggests that planets beyond the traditional habitable zone of a star could still offer environments conducive to life. This kind of discovery would shift the criteria for what makes a planet habitable. It highlights that life doesn't necessarily need to depend on proximity to a star, but can instead rely on alternative energy sources, such as geothermal heat. Planet Nine's influence on the outer solar system also connects to the search for life in the broader universe. Understanding how large, distant planets affect smaller bodies and their orbits could help refine the search for exoplanets with life-supporting conditions. If Planet 9 exists, its discovery could lead to new models for identifying life-supporting environments on other planets. By studying its potential composition and atmosphere, we may gain clues about how life might survive in harsh, remote conditions. The study of distant planets like Planet 9 informs astrobiologists about the diversity of environments where life might exist. It encourages the exploration of planets and moons that might not traditionally be considered habitable, but could harbour life under the right circumstances. Research into the potential of Planet 9 could reveal more about the conditions necessary for life to thrive in extreme environments. Whether through the discovery of subsurface oceans or atmospheric chemistry, its study would provide valuable lessons for astrobiology. Planet 9's search brings attention to the broader implications for life beyond Earth. By focusing on how planets form and what conditions they can support, we refine the criteria used to search for life elsewhere in the cosmos. By exploring the possibility of life on planets far from their star, the discovery of Planet 9 could encourage a more inclusive approach to the search for life. It demonstrates that habitability might not always conform to traditional definitions, opening up new avenues for exploration. Through the ongoing search for Planet 9, astronomers and astrobiologists can learn more about the fundamental requirements for life. This knowledge can ultimately guide us in identifying other worlds, potentially far beyond our solar system, where life could exist. Upcoming advancements in telescope technology are expected to significantly enhance the search for Planet 9. New innovations in infrared and adaptive optics will allow telescopes to detect faint objects in previously unreachable areas of the sky. The development of larger and more sensitive telescopes will increase our ability to survey vast regions with higher precision. These telescopes will provide the necessary tools to spot slow-moving distant objects like Planet 9 more effectively. Next-generation space-based telescopes, such as the James Webb Space Telescope, will bring unparalleled resolution and sensitivity to infrared observations. These advancements will help identify the faint heat signatures of distant planets, even those far beyond Neptune. Ground-based observatories are also set to benefit from technological upgrades. The use of advanced adaptive optics will improve image clarity, reducing the distortion caused by Earth's atmosphere and enabling sharper observations of distant objects. The implementation of artificial intelligence and machine learning in astronomy will transform how we analyze telescope data. These technologies can quickly sift through massive amounts of data, identifying potential candidates for Planet 9 more efficiently than ever before. Increased collaboration between observatories worldwide will allow for more coordinated efforts. By combining data from multiple sources and enhancing observational strategies, scientists will be able to focus their efforts on more promising regions of the sky. Innovations in survey techniques, such as wide-field surveys with specialized cameras, will improve the coverage of large portions of the sky. These new tools will increase the likelihood of detecting faint, distant objects like Planet 9 across a wider area. The development of next-generation spectrometers will allow astronomers to analyze the composition of distant objects with greater precision. By studying the light reflected from these objects, scientists can infer their characteristics and better understand their potential for supporting life. Further advancements in telescope resolution and data processing will enable astronomers to observe objects in unprecedented detail. This could provide new insights into the structure of distant regions of the solar system and help refine the search for Planet 9. Increased funding and international cooperation will drive the creation of more powerful telescopes, both ground-based and space-based. These advancements will create new opportunities for discovery, accelerating the search for hidden planets and other celestial bodies. Technological innovations in robotic observatories will enable more frequent and extensive monitoring of specific regions of the sky. This could help uncover faint objects that might otherwise remain undetected, improving our chances of locating Planet 9. The rapid pace of technological progress in astronomy promises to change the landscape of planetary discovery. With these upcoming advancements, the search for Planet 9 is more promising than ever, bringing us closer to uncovering the secrets of our solar system. International collaboration plays a crucial role in the quest for deeper space exploration, particularly in the search for elusive objects like Planet 9. By pooling resources and expertise, space agencies around the world can work together to tackle the challenges of exploring the far reaches of our solar system. Joint missions involving multiple countries bring together a wide range of specialized knowledge. This diversity of expertise allows for more innovative solutions and ensures that all aspects of planetary exploration are covered, from telescope design to data analysis. Global partnerships also help secure funding for large-scale projects. Space exploration is an expensive endeavor, and by sharing the costs, international collaborations make ambitious missions more feasible and increase the likelihood of success. Working together, countries can coordinate their efforts to monitor different regions of the sky, optimizing the chances of detecting faint, distant objects like Planet 9. This level of cooperation ensures that no part of the sky is overlooked in the search for new discoveries. International teams also bring a variety of perspectives to the table, which can lead to novel ideas and strategies. Different countries often have different technological capabilities, and by combining these strengths, they can build more powerful tools for deep space exploration. One key example of international collaboration is the cooperation between NASA, ESA, and other space agencies on various space telescopes. Their shared resources and joint research efforts have resulted in the development of instruments that are far more advanced than any one country could achieve on its own. Collaborative missions allow scientists from different nations to contribute their findings and analysis, creating a global database of astronomical data. This shared knowledge helps ensure that discoveries are made more efficiently and are available for further study worldwide. International space exploration also facilitates the development of cutting-edge technology. By working together, countries can push the boundaries of what's possible, developing new instruments, spacecraft, and even techniques that can be used in the search for Planet 9 and beyond. Cooperation among space agencies also allows for faster and more effective communication. When a significant discovery is made, international teams can quickly exchange data, ensuring that all scientists involved can begin analyzing it as soon as possible. In the search for distant planets like Planet 9, international collaboration means that more ground can be covered in less time. Teams working from different locations around the world can coordinate their observations, ensuring that they don't miss any potential targets. The combined power of international collaboration also enables the creation of ambitious space missions that can explore distant regions of the solar system. By working together, space agencies can launch missions that reach farther and dive deeper into uncharted territories, revealing secrets that would otherwise remain hidden. As the search for Planet 9 and other deep space objects continues, international cooperation will remain a cornerstone of exploration. By uniting the strengths and knowledge of space agencies worldwide, we can push the limits of our understanding and make new discoveries that benefit all of humanity. The search for Planet 9 has the potential to uncover a wealth of new discoveries in the Kuiper belt and beyond. This distant region of our solar system remains largely unexplored, and hidden objects could offer crucial insights into the formation and evolution of planetary systems. Many small bodies in the Kuiper belt may be influenced by Planet 9's gravitational pull, and their orbits could provide valuable data. These objects could help scientists learn more about the early solar system and the forces that shaped it. As we search for Planet 9, we might also uncover previously unknown dwarf planets, icy bodies, or even moons of larger objects. The Kuiper belt is full of mysteries, and each new discovery helps to piece together the puzzle of our solar system's outer reaches. Beyond the Kuiper belt, there may be even more distant regions waiting to be explored. The scattered disk, for example, holds objects that are even farther from the Sun, and Planet 9's influence could reveal more about this remote area. Planet 9's potential discovery could also help astronomers find other unknown planets or large objects in the outer solar system. Its gravitational effects on nearby bodies could guide searches for additional large planets beyond Neptune, expanding our understanding of the solar system's boundaries. The ongoing search could reveal new classes of objects that were previously undetected. For instance, Planet 9 might provide clues about the existence of cold, icy planets or moons that could harbor conditions for life in ways we haven't imagined. Every new discovery in the Kuiper belt helps scientists refine models of planetary formation. The presence of unknown objects or previously undetected bodies could challenge existing theories and lead to new understanding of how our solar system came to be. The outer solar system is also home to many comets and other transient objects. By studying their interactions with Planet 9 or other distant bodies, we could learn more about the behavior of comets and their role in delivering materials across the solar system. Objects in the Kuiper belt and beyond could provide valuable analogues for studying exoplanets. By comparing these distant objects to planets in other star systems, astronomers may gain insights into planetary formation processes that are universal across the galaxy. The potential discovery of Planet 9 might also inspire missions to explore the outer solar system directly. These missions could provide the first close-up images of distant Kuiper belt objects, revealing details about their composition, structure, and potential for future exploration. Through the search for Planet 9, we may unlock entirely new categories of celestial objects that have remained hidden until now. These discoveries could offer key insights into the solar system's early history and its ongoing evolution. Each step forward in the search for Planet 9 opens the door to even more discoveries. As we explore the distant reaches of our solar system, new mysteries will inevitably arise, expanding our knowledge of the cosmos in ways we can't yet fully anticipate. As new data from space telescopes and ground-based observatories continues to emerge, the Planet 9 hypothesis is being re-evaluated. The discovery of new objects in the outer solar system and improved modeling techniques may provide fresh evidence that strengthens or challenges the theory. Recent findings of additional trans-Neptunian objects have sparked renewed interest in Planet 9. The clustering and orbital alignments of these distant bodies are being closely examined to determine if they align with predictions made by the hypothesis. Advancements in telescope technology allow astronomers to gather more detailed observations, which could either confirm or disprove the existence of Planet 9. The increased sensitivity of infrared instruments is key to detecting faint objects like Planet 9, especially in the outer solar system. With each new dataset, astronomers are refining their models of Planet 9's orbit. These updated models incorporate more precise measurements, helping to predict where Planet 9 might be located and how it influences nearby objects. The detection of additional anomalies in the Kuiper belt could provide further clues about the existence of a ninth planet. As more objects are discovered in this region, scientists are reassessing the gravitational effects that could indicate the presence of a massive unseen world. As the understanding of gravitational dynamics improves, researchers are revisiting old assumptions about the solar system's outer reaches. This new perspective is opening up the possibility that Planet the Ninth may be even closer, more massive, or in a different orbit than previously thought. Refining the statistical models used to predict the planet's location is a significant focus of current research. As more data becomes available, these models are becoming more sophisticated, allowing astronomers to target specific regions of the sky for further investigation. The improved accuracy of simulations is helping to narrow down the search area for Planet 9. The more precise the models, the better the chance of detecting this elusive planet with current and future observational tools. New theoretical work is also being done to explore alternative explanations for the observed anomalies in the outer solar system. These competing ideas are being tested against the existing data to determine which one best explains the observations. In parallel with the search for Planet 9, discoveries in the field of exoplanets are providing valuable insights into planetary formation and migration. This growing body of knowledge is helping astronomers rethink how planets could form in the outer regions of our solar system. The ongoing analysis of previously collected data, combined with the latest observations, is continuously reshaping the Planet 9 hypothesis. New evidence could either support the existence of this hypothetical planet or suggest that the anomalies in the Kuiper belt have another cause. As new technologies and more refined methods of observation become available, astronomers are in a better position than ever to revisit and test the Planet 9 hypothesis. Each new discovery adds a piece to the puzzle, bringing the mystery of Planet 9 closer to resolution. The prospects for confirming the existence of Planet 9 are becoming more promising as new observational tools come online. Advanced telescopes with increased sensitivity and wider fields of view are helping astronomers search larger portions of the sky more efficiently. The use of infrared telescopes, both ground-based and space-based, is key to detecting faint objects like Planet 9. These instruments can capture the weak thermal radiation emitted by distant objects, providing a pathway to uncovering this hidden world. As astronomers refine their models of Planet 9's expected orbit, the search area is becoming more focused. This precision in targeting specific regions of the sky increases the chances of detection and brings us closer to confirming its presence. One of the most promising avenues for detection is through the study of trans-Neptunian objects. The gravitational influence of Planet 9 on the orbits of these distant bodies may offer a clear indication of its existence, even if the planet itself remains hidden. International collaboration is also improving the prospects for detection. By pooling resources and sharing data from different observatories, astronomers can cast a wider net and increase the likelihood of spotting Planet 9 in the vastness of space. Citizen science projects are providing additional support for the search. Volunteers help analyze large data sets, allowing professional astronomers to focus on the most promising leads and speeding up the search for faint objects like Planet 9. Ongoing space missions, such as the James Webb Space Telescope, offer significant advancements in our ability to detect distant planets. Its advanced infrared capabilities make it one of the most promising tools for locating Planet 9. The search for Planet 9 also benefits from improvements in computational modeling. As simulations become more accurate, astronomers can predict the planet's position with greater certainty, narrowing the search area and improving the odds of detection. Astronomers are also looking for signs of Planet 9's gravitational influence on the orbits of other distant objects, such as comets. These subtle disturbances in their paths could serve as a strong indicator that a massive planet is lurking in the outer solar system. The development of more powerful and specialized instruments is enhancing the ability to detect objects at vast distances. These advancements allow for deeper exploration of the outer solar system, making the confirmation of Planet 9's existence a real possibility in the near future. As technology continues to advance, the gap between hypothesis and confirmation continues to shrink. New breakthroughs in observational techniques and data analysis will play a critical role in providing the evidence needed to confirm Planet 9's existence. The prospects for confirming Planet 9's existence are brighter than ever. As telescopes and computational models evolve, the search becomes more precise, offering new hope that this mysterious planet will soon be discovered. In this video, we explored the fascinating and ongoing search for Planet 9, one of the most mysterious objects in our solar system. We discussed the history behind the hypothesis, the scientists involved in developing the theory, and the observational anomalies that have sparked interest in its existence. We also delved into how mathematical models have predicted its size, mass, and orbital properties, as well as the skepticism surrounding its existence. The potential impact of Planet 9 on the outer solar system was highlighted, including its gravitational effects on objects in the Kuiper belt and the possibility of influencing comet trajectories. We explored the technological advancements in telescopes and infrared detection methods that are driving the search forward. These innovations, alongside the power of international collaboration, are making the detection of faint objects like Planet 9 more feasible than ever before. Citizen science and future space missions were also identified as key components in the hunt for this elusive planet. Additionally, we covered the broader implications of Planet 9's discovery, including its potential to reshape our understanding of the solar system, planetary formation, and even the criteria for habitable zones. The prospect of finding new, previously unknown objects in the outer solar system was also discussed, further adding to the excitement surrounding the search. As new data comes in and technologies continue to evolve, the possibility of confirming Planet 9's existence seems more promising. Astronomers around the world are now more focused than ever on pinpointing its location and understanding its impact on the solar system. With continued advancements and collaborative efforts, the discovery of Planet 9 could be just around the corner. If you enjoyed learning about the search for Planet 9 and its implications, be sure to like and subscribe to our channel. Your support helps us bring more interesting topics like this one to you. Don't forget to check out the rest of our videos, where we explore other mysteries of the universe, cutting-edge scientific discoveries, and more. By subscribing, you'll stay updated on all our future content and be part of a community passionate about learning and exploring the cosmos. We're excited to continue sharing these fascinating topics with you. Thank you for watching, and we hope this video has sparked your curiosity about the mysteries of the solar system and beyond. Be sure to leave your thoughts and questions in the comments section below. We love hearing from you. Stay tuned for more videos that dive into some of the most intriguing questions in science and space. Until then, keep exploring and keep wondering what's out there waiting to be discovered.